Learning objectives. In this chapter, the user would learn the following in detail: frequency analysis, continuous time signals, and discrete time signals. Properties of the Fourier transform for discrete time signals. Frequency domain, characteristics of LTI systems. LTI system as a frequency selective filter, inverse systems and deconvolution. Frequency analysis of discrete time signals. The Fourier series representation of a continuous time periodic signal can consist of an infinite number of frequency components where the frequency spacing between two successive harmonically related frequencies is 1 divided by Tp, and where Tp is the fundamental period. Since the frequency range for continuous time signal extends from minus infinity to plus infinity, it is possible to have signals that contain an infinite number of frequency components. The frequency range for discrete time signals is unique over the interval minus pi comma pi or 0 comma 2 pi. A discrete time signal of fundamental period n can consist of frequency components separated by 2 pi by n radians or f equal to 1 by n cycles. The Fourier series representation of a discrete time periodic signal will contain at most n frequency components. The Fourier series for discrete time periodic signals: a periodic sequence x of n with period n, that is capital X of n equal to small x of n plus capital N. For all n, the Fourier series representation for x of n consists of n exponential functions e power j 2 pi k n divided by capital N, where k equal to 0, 1, etc., capital N minus 1, and is expressed as x of n equal to summation k equal to 0 to capital N minus 1 ck into e power j 2 pi kn divided by n is called example 1, where the ck are the coefficients in the series representation. To derive the expression for the Fourier coefficients, we use the following formula: summation n equal to 0 to capital N minus 1 e power j 2 pi kn divided by n equal to capital N for k equal to 0, plus or minus 1, plus or minus 2n, etc., and 0 otherwise, is called example 2. Applying the geometric summation formula, summation n equal to 0 to capital N minus 1, an equal to capital N when a equal to 1, 1 minus a power capital N divided by 1 minus a, when a not equal to 1. The expression for the Fourier coefficients ck can be obtained by multiplying both sides of example 1 by exponential e power minus j 2 pi n divided by n, and summing product from n equal to 0 to capital N minus 1. Thus, summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi ln divided by n equal to summation n equal to 0 to capital N minus 1 into summation k equal to 0 to capital N minus 1 ck into e power j 2 pi k minus l n divided by n. If we perform the summation over the n first in the right side of above equation, we obtain summation n equal to 0 to capital N minus 1 e power j 2 pi k minus l n divided by capital N equal to capital N, where k minus 1 equal to 0, plus or minus n, plus or minus 2n, and 0 otherwise, where we have made use of example 2. Therefore, the right side reduces to NCL, and NCL equal to 1 divided by capital N into summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi l n divided by capital N, where l equal to 0, 1, etc., capital N minus 1. Thus we have the desired expression for the Fourier coefficients in terms of the signal x of n. Synthesis equation: x of n equal to summation k equal to 0 to capital N minus 1 ck into e power j 2 pi kn divided by capital N. Analysis equation: ck equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi kn divided by capital N. Frequency analysis of discrete time periodic signals. The synthesis equation is often called the discrete time Fourier series DTFS. The Fourier coefficient Ck, where k equal to 0, 1, etc. capital N minus 1 provide the description of x of n. In the frequency domain, Ck represents the amplitude and phase associated with the frequency component. Sk of n equal to e power j 2k pi n divided by capital N equal to e power j omega kn, where omega k equal to 2 pi k divided by capital N. The functions sk of n are periodic with period capital N. Hence, sk of n equal to sk of n plus capital N. From analysis equation, which holds for every value of k, we have ck plus capital N equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi of k plus capital N into n divided by capital N equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi k small n divided by capital N equal to ck. The Fourier series coefficients Ck from a periodic sequence when extended outside of the range k equal to 0, 1, etc. capital N minus 1. Hence, Ck plus capital N equal to Ck. That is, Ck is a periodic sequence with the fundamental period capital N. The spectrum of a signal x of n, which is periodic with period capital N, is a periodic sequence with period capital N. Any capital N consecutive samples of the signal or its spectrum provide a complete description of the signal in the time or frequency domains. The frequency range minus pi less than omega k equal to 2 pi k divided by capital N less than or equal to pi, corresponding to minus n by 2 less than or equal to k less than or equal to n by 2, creates an inconvenience when capital N is odd. Power density spectrum of periodic signals. The average power of a discrete time periodic signal with period capital N is defined as Px equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 modulus of x of n the whole square. We shall now derive an expression for Px in terms of the Fourier coefficient Ck. Using the synthesis equation in above equation, we have Px equal to 1 divided by n summation n equal to 0 to capital N minus 1 x of n into x star of n equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 x of n into summation k equal to 0 to capital N minus 1 ck star into e power minus j 2 pi kn divided by capital N. Interchanging the order of the two summations and making use of analysis equation, we obtain Px equal to summation k equal to 0 to capital N minus 1 ck star into 1 by n summation n equal to 0 to capital N minus 1 x of n into e power minus j 2 pi kn divided by capital N equal to summation k equal to 0 to capital N minus 1 modulus of ck the whole square equal to 1 divided by capital N summation n equal to 0 to capital N minus 1 modulus of x of n the whole square. The average power in the signal is the sum of the powers of the individual frequency components. The sequence modulus of Ck the whole square for k equal to 0, 1, etc. capital N minus 1 is a distribution of power as a function of frequency and is called the power density spectrum of the periodic signal. The energy of the sequence x of n over a single period En equal to summation n equal to 0 to capital N minus 1 modulus of x of n the whole square equal to n into summation k equal to 0 to capital N minus 1 modulus of Ck the whole square. If the signal x of n is real, then Ck star equal to C minus k, or modulus of C minus k equal to modulus of Ck for even symmetry minus angular point C minus k equal to angular point Ck for odd symmetry. By combining above equations, we obtain modulus of Ck equal to modulus of C capital N minus k and del angular point Ck equal to minus angular point C capital N minus k. More specifically, we have if n is even, modulus of C naught equal to modulus of Cn, modulus of C1 equal to modulus of Cn minus 1, modulus of Cn by 2 equal to modulus of Cn divided by 2, modulus of Cn minus 1 divided by 2 equal to modulus of Cn plus 1 divided by 2. If n is odd, angular point C naught equal to minus angular point Cn equal to 0, angular point C1 equal to minus angular point Cn minus 1, angular point Cn by 2 equal to angular point 0, angular point Cn minus 1 divided by 2 equal to minus angular point Cn plus 1 divided by 2. For a real single, the spectrum Ck, k equal to 0, 1, etc. n by 2. For n even, or k equal to 0, 1, etc. n minus 1 divided by 2 for n odd, completely specifies the signal in the frequency domain. Highest relative frequency that can be represented by a discrete time signal is equal to pi. Fourier series can also be expressed as x of n equal to C naught plus 2 times of summation k equal to 0 to L modulus of Ck into cos of 2 pi by n into kn plus theta k equal to a naught plus summation k equal to 1 to L ak into cos 2 pi by n into kn minus bk sin 2 pi by n into kn, where a naught equal to C naught, ak equal to 2 times of modulus of Ck into cos theta k, bk equal to 2 into modulus of Ck sin theta k, and L equal to n divided by 2 if n is even, and L equal to n minus 1 divided by 2 if n is odd. As in the case of continuous time signals, the power density spectrum modulus of Ck the whole square does not contain any phase information. The spectrum is discrete and periodic with a fundamental period equal to that of the signal itself. The Fourier transform of discrete time periodic signals. As in the case of continuous time aperiodic energy signals, the frequency analysis of discrete time aperiodic finite energy signals involves a Fourier transform of the time domain signal. The Fourier transform of a finite energy discrete time signal x of n is defined as x of omega equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n. X of omega represents the frequency content of the signal x of n. In other words, x of omega is a decomposition of x of n into its frequency components. Two basic differences between the Fourier transform of a discrete time finite energy signal and the Fourier transform of a finite energy analog signal. Difference 1. For continuous time signals, The spectrum of the signal have a frequency range of minus infinity to infinity. In contrast, the frequency range for a discrete time signal is unique over the frequency interval of minus pi to pi or 0 to 2 pi. This property is reflected in the Fourier transform of the signal. X of omega is periodic with period 2 pi. X of omega plus 2 pi k equal to summation n equal to minus infinity to plus infinity x of n into e power minus j of omega plus 2 pi k n equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n into e power minus j 2 pi k n equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n equal to x of omega. Difference 2. Since the signal is discrete in time, the Fourier transform of the signal involves a summation of terms instead of an integral, as in the case of continuous time signals. Frequency analysis of discrete time periodic signals. Synthesis equation inverse transform. X of n equal to 1 divided by 2 pi integral 2 pi x of omega into e power j omega n into d omega. Analysis equation direct transform. X of omega equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n. Convergence of the Fourier transform. In the derivation of the inverse transform given by synthesis equation inverse transform, xn of omega equal to summation n equal to minus n to n x of n into e power minus j omega n converges uniformly to x of omega given in the integral as n tends to infinity. By uniform convergence we mean that for each omega limit n tends to infinity, supremum of omega x of omega minus xn of omega equal to 0. Uniformly convergence is guaranteed if x of n is absolutely summable. Indeed, if summation n equal to minus infinity to plus infinity modulus of x of n less than infinity, then modulus of x of omega equal to modulus of summation n equal to minus infinity to plus infinity x of n into e power minus j omega n less than or equal to summation n equal to minus infinity to plus infinity modulus of x of n less than infinity. Hence, summation n equal to minus infinity to plus infinity modulus of x of n less than infinity is a sufficient condition for the existence of the discrete time Fourier transform. This is the discrete time counterpart of the third Dirichlet condition for the Fourier transform of the continuous time signals. The first two conditions do not apply due to the discrete time nature of x of n. Some sequences are not absolutely summable, but they are square summable, that is, they have finite energy. Ex equal to summation n equal to minus infinity to plus infinity modulus of x of n the whole square less than infinity. A mean square convergence condition. Limit n tends to infinity integral minus pi to plus pi modulus of x of omega minus xn of omega the whole square d omega equal to 0. Thus the energy in the error x of omega minus xn of omega tends towards 0, but the error x of omega minus xn of omega does not necessarily tend to 0. Energy density spectrum of aperiodic signals. The energy of a discrete time signal x of n is defined as Ex equal to summation n equal to minus infinity to plus infinity modulus of x of n the whole square. Let us now express the energy Ex in terms of the spectral characteristics x of omega. Ex equal to summation n equal to minus infinity to plus infinity x of n into x star n equal to summation n equal to minus infinity to plus infinity x of n into within the bracket 1 by 2 pi integral minus pi to pi x star of omega into e power minus j omega n d omega. If we interchange the order of integration and summation in the equation above, we get Ex equal to 1 divided by 2 pi integral minus pi to pi x star of omega into summation n equal to minus infinity to plus infinity x of n into e power minus j omega n into d omega equal to 1 by 2 pi integral minus pi to modulus of x of omega the whole square into d omega. Therefore, the energy relation between x of n and x of omega is Ex equal to summation n equal to minus infinity to plus infinity modulus of x of n the whole square equal to 1 divided by 2 pi integral minus pi to pi modulus of x of omega the whole square into d omega. This is Parseval's relation for discrete time aperiodic signals with finite energy. The spectrum x of omega is in general a complex valued function of frequency x of omega equal to modulus of x of omega into e power j theta of omega, where theta of omega equal to angular point x of omega is the phase spectrum and modulus of x of omega is the magnitude spectrum. As in case of continuous time signals, the quantity Sxx of omega equal to modulus of x of omega the whole square represents the distribution of energy as a function of frequency, and it is called the energy density spectrum of x of n. Sxx of omega does not contain any phase information. Suppose signal x of n is real, x star of omega equal to x of minus omega, or modulus of x of minus omega equal to modulus of x of omega, even symmetry, and angular point x of minus omega equal to minus angular point of x of omega is called out symmetry. From above continuous time signal equation, it follows that Sxx of minus omega equal to Sxx of omega is called even symmetry. The frequency range of real discrete time signals can be limited further to the range 0 less than or equal to omega less than or equal to pi. The frequency domain description of a real discrete time signal is completely specific if its spectrum in the frequency range 0 less than or equal to omega less than or equal to pi. Relationship of the Fourier transform to the Z transform. The Z transform of a sequence x of n is defined as x of z equal to summation n equal to minus infinity to plus infinity x of n into z power minus n, with region of convergence R2 less than modulus of z less than R1, where R2 less than modulus of z less than R1 is the region of convergence x of z. Let us express the complex variable z in polar form as z equal to r into e power j omega, where r equal to modulus of z and omega equal to angular point z. Then within the region convergence of x of z, we can substitute z equal to r into e power j omega into x of z equation. This yields x of z, where z equal to r into e power j omega equal to summation n equal to minus infinity to plus infinity x of n into r power minus n into e power minus j omega n. From the relationship in above equation, we note that x of z can be interpreted as the Fourier transform of the signal x of n into r power minus n. The weighting factor r power minus n is growing with n if r less than 1 and decaying if r greater than 1. If x of z converges for modulus of z equal to 1, then x of z, where z equal to r into e power j omega equivalent to x of omega equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n. Therefore, the Fourier transform can be viewed as the Fourier transform of the sequence evaluated on the unit circle. If x of z does not converge in the region modulus of z equal to 1, the Fourier transform x of omega does not exist. The existence of the z transform requires that the sequence modulus of x of n into r power minus n be absolutely summable for some value of r, that is summation n equal to minus infinity to plus infinity modulus of x of n into r power minus n less than infinity. Hence, if above equation converges only for values of r greater than r naught greater than 1, the z transform exists but the Fourier transform does not exist. The existence of the z transform requires that above equation be satisfied for some region in the z plane. If this region contains the unit circle, the Fourier transform x of omega exists. The existence of the Fourier transform, which is defined for the finite energy signals, does not necessarily ensure the existence of the z transform. The substrum. X of n is a sequence having a z transform x of z. X of n is a stable sequence so that x of z converges on the unit circle. The complex spectrum of the sequence modulus of x of n is defined as the sequence Cx of n, which is the inverse z transform Cx of z, where Cx of z equal to ln x of z. The complex spectrum exists if Cx of z converges in the angular region r1 less than modulus of z less than r2, where 0 less than r1 less than 1 and r2 greater than 1. Within this region of convergence, Cx of z can be represented by the Laurent series Cx of z equal to ln x of z equal to summation n equal to minus infinity to plus infinity Cx of n into z power minus n, where Cx of n equal to 1 divided by 2 pi j integral c ln x of z z power n minus 1 into dz. C is a closed contour about the origin and lies within the region of convergence. Clearly, if Cx of z can be represented as above, the complex spectrum sequence Cx of n is stable. Furthermore, if the complex spectrum exists, Cx of z converges on the unit circle, and hence we have Cx of omega equal to ln x of omega equal to summation n equal to minus infinity to plus infinity Cx of n into e power minus j omega n, where Cx of n is the sequence obtained from the inverse Fourier transform of ln x of omega, that is Cx of n equal to 1 divided by 2 pi integral minus pi to pi ln x of omega into e power j omega n into d omega. If we express x of omega in terms of its magnitude and phase, x of omega equal to modulus of x of omega e power j theta of omega, then ln x of omega equal to ln modulus of x of omega plus j theta of omega. By substituting ln x of omega in Cx of n, we obtain the complex spectrum in the form Cx of n equal to 1 divided by 2 pi integral minus pi to pi ln modulus of x of omega plus j theta of omega into e power j omega n d omega. We can separate the inverse Fourier transform in above equation into the inverse Fourier transforms of ln modulus of x of omega and theta of omega. Cm of n equal to 1 divided by 2 pi integral minus pi to pi ln x of omega into e power I omega n d omega, and c theta of n equal to 1 divided by 2 pi integral minus pi to pi theta of omega into e power I omega theta into d omega. In some applications like speech signal processing, only the component Cm of n is computed. In such a case, the phase of x of omega is ignored. Therefore, the sequence modulus of x of n cannot be recovered from modulus of Cm of n. The information from modulus of x of n to modulus of Cm of n is not invertible. In speech signal processing, the real spectrum has been used to separate and thus to estimate the spectral content of the speech from the pitch frequency of the speech. The complex spectrum is used in practice to separate signals that are convolved. The process of separating two convolved signals is called homomorphic deconvolution. The Fourier transform of signals with poles on the unit circle. The Fourier transform of a sequence x of n can be determined by evaluating its z transform x of z on the unit circle, provided that the unit circle lies within the region of convergence of x of z. Otherwise, the Fourier transform does not exist. There are some aperiodic sequences that are neither absolutely summable nor square summable. Hence, their Fourier transforms do not exist. One such sequence is the unit step sequence which has the z transform x of z equal to 1 divided by 1 minus z power minus 1. Another such sequence is the causal sinusoidal signal sequence x of n equal to cos omega naught n into u of n. This sequence has the z transform x of z equal to 1 minus z power minus 1 cos omega naught divided by 1 minus 2 into z power minus 1 into cos omega naught plus z power minus 2. Note that both of these sequences have poles on the unit circle. For sequences such as these two examples, it is sometimes useful to extend the Fourier transform representation. This can be accomplished in a mathematically rigorous way by allowing the Fourier transform to contain impulses at certain frequencies corresponding to the location of the poles of x of z that lie on the unit circle. The impulses are functions of the continuous frequency variable r omega and have infinite amplitude, zero width and unit area. An impulse can be viewed as the limiting form of a rectangular pulse of height 1 by a and width a in the limit as a tends to 0. Thus, by allowing impulses in the spectrum of a signal, it is possible to extend the Fourier transform representation to some signal sequences that are neither absolutely summable nor square summable. The sampling theorem revisited. To process a continuous time signal using digital signal processing techniques, it is necessary to convert the signal into a sequence of numbers. This is usually done by sampling the analog signal, say x0 of t, periodically every t seconds to produce a discrete time signal x of n, given by x of n equal to xa of nt, where minus infinity less than n less than infinity. The relationship above describes the sampling process in the time domain. The sampling frequency fx equal to 1 divided by 2 must be selected large enough such that the sampling does not cause any loss of spectral information. Indeed, if the spectrum of the analog signal can be recovered from the spectrum of the discrete time signal, there is no loss of information. Consequently, we investigate the sampling process by finding the relationship between the spectra of signals x0 of t and x of n. If x0 of t is an aperiodic signal with a finite energy, its voltage spectrum is given by Fourier transform relation xa of f equal to integral minus infinity to plus infinity xa of t into e power minus j 2 pi ft into dt. Whereas the signal x0 of t can be recovered from its spectrum by the inverse Fourier transform xa of t equal to integral minus infinity to plus infinity xa of f e power j 2 pi ft df. The utilization of all frequency components in the infinite frequency range minus infinity less than f less than infinity is necessary to recover the signal xa of t if the signal is not band limited. The spectrum of a discrete time signal x of n obtained by sampling xi of t is given by the Fourier transform relation x of omega equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n, or x of f equal to summation n equal to minus infinity to plus infinity x of n into e power minus j 2 pi fn. The sequence x of n can be recovered from its spectrum x of omega or x of f by the inverse transfer x of n equal to 1 divided by 2 pi integral minus pi to pi x of omega into e power I omega n into d omega equal to integral minus 1 by 2 to 1 by 2 x of f into e power j 2 pi by n into df is called equation number 4.2.1. In order to determine the relationship between the spectra of the discrete time signal and the analog signal, we note that periodic sampling imposes a relationship between the independent variables t and n in the signals xi of t and x of n respectively. That is, t equal to nt equal to n by f1 is called equation number 4.2.2. This is a relationship in the time domain implies a corresponding relationship between the frequency variables f and f in xi of f and x of f respectively. X of n equivalents to xi of nt equal to integral minus infinity to plus infinity xi of f into e power j 2 pi n f by fs into df is called equation number 4.2.3. If we compare 4.2.1 with the 4.2.3, we conclude that integral minus 1 by 2 to plus 1 by 2 x of f into e power j 2 pi fn into df equal to integral minus infinity to plus infinity xi of f into e power j 2 pi n f divided by fs into df is called equation number 4.2.4. The periodic sampling imposes a relationship between the frequency variables f and f of the corresponding analog and discrete time signals respectively, that is, f equal to f divided by fs. With the aid of above relation, we can make a simple change in variable in equation number 4.2.4 and obtain the result 1 divided by fs integral minus fs by 2 to plus fs by 2 x of f divided by fs into e power j 2 pi f by fs into df equal to integral minus infinity to plus infinity x a of f into e power j 2 pi f by fs into df. The integration range of the integral on the right hand side can be divided into an finite number of intervals of width fs. Thus, the integral over the infinite range can be expressed as a sum of integrals. Integral minus infinity to plus infinity xi of f into e power j 2 pi f by fs into df equal to summation k equal to minus infinity to plus infinity integral k minus 1 by 2 into fs to k plus 1 by 2 into fs xi of f into e power j 2 pi n f by fs into df is called equation number 4.2.5. xi of f in the frequency interval k minus 1 by 2 into fs to k plus 1 by 2 into fs is identical to xi of f minus kfs in the interval minus fs by 2 to fs by 2 summation k equal to minus infinity to plus infinity integral k minus 1 by 2 into fs to k plus 1 by 2 into f into fs xi of f into e power j 2 pi n f by fs into df equal to summation k equal to minus infinity to plus infinity integral minus fs by 2 to plus fs by 2 xi of f minus kfs into e power j2 pi n f by fs into df equal to integral minus fs by 2 to plus fs by 2 summation k equal to minus infinity to plus infinity xi of f minus kfs e power I2 pi n f by fs into df. We have used periodicity of exponential e power j2 pi n f plus kfs divided by fs equal to e power j2 pi n f by fs. Comparing equation 4.2.6, 4.2.5 and 4.2.4, we conclude x of f by fs equal to fs into summation k equal to minus infinity to plus infinity xi of f minus kfs is called equation number 4.2.7, or x of f equal to fs of summation k equal to minus infinity to plus infinity xi of f minus k into f of s is called equation number 4.2.8. Sampling theorem. A bandwidth continuous time signal with the highest frequency bits can be uniquely recovered from its samples provided that the sampling rate fs greater than or equal to 2b samples per second. According to the sampling theorem and the reconstruction formula, the recovery of x naught of t from its samples x of n requires an infinite number of samples. Frequency domain classification of signals. The concept of bandwidth. If a power signal has its power density spectrum concentrated about zero frequency, such a signal is called a low frequency signal. If the signal power density spectrum is concentrated at high frequencies, the signal is called a high frequency signal. A signal having a power density spectrum concentrated somewhere in the broad frequency range between low frequency and high frequency, it is called a medium frequency signal or a band pass signal. A discrete time finite energy signal x of n is said to periodically band limited if modulus of x of omega equal to 0 for omega naught less than modulus of omega less than n. Similarly, a periodic continuous time signal xp of t is periodically band limited if its Fourier coefficients ck equal to 0 for modulus of k greater than m, where m is some positive integer. A signal x of t will be called time limited if x of t equal to 0. If the signal is periodic with period Tp, it will be called periodically time limited if xp of t equal to 0. Some examples of band limiter signals. The frequency ranges of some natural signals. We can see in the table what are the types of signal and the frequency range. Frequency ranges of some biological signals. A graphic recording of retina characteristics. B. A graphic recording of involuntary movement of the eyes. C. A graphic recording of respiratory activity. D. A graphic recording of muscular action such as muscular contraction. E. A recording of blood pressure. Frequency ranges of some seismic signals. Frequency ranges of electromagnetic signals. Physical and mathematical dualities. The following frequency analysis tools have been introduced. The Fourier series for continuous time periodic signals, the Fourier transform for continuous time aperiodic signals, the Fourier series for discrete time periodic signals, the Fourier transform for discrete time aperiodic signals. Continuous time signals have aperiodic spectra. A close inspection of Fourier series and Fourier transform analysis formulas for continuous time signals does not reveal any kind of periodicity in the spectral domain. The frequency range of continuous time signals extends from f equal to 0 to f equal to infinity. Discrete time signals have periodic spectra. Both the Fourier series and the Fourier transform for discrete time signals are periodic with period omega equal to 2 pi. As a result of this periodicity, the frequency range of discrete time signals is finite. Periodic signals have discrete spectra. Periodic signals are described by means of Fourier series. The Fourier series coefficients provide the lines that constitute the discrete spectrum. A periodic finite energy signals have continuous spectra. This property is direct consequence of the fact that both x of f and x of omega are functions of expectation of j2 pi ft and expectation of j omega n respectively, which are continuous functions of the variables f and omega. The continuity in frequency is necessary to break the harmony and thus create a periodic signals. The periodicity with period a in one domain automatically implies discretization with spacing of 1 by a in the other domain and vice versa. We observe dualities between following analysis and the synthesis equations. Number 1. The analysis and synthesis equations of the continuous time Fourier transform. Number 2. The analysis and synthesis equations of the discrete time Fourier transform. Number 3. The analysis equation of the continuous time Fourier series and the synthesis equation of the discrete time Fourier transform. Number 4. The analysis equation of the discrete time Fourier transform and the synthesis equation of the continuous time Fourier series. Analysis of analysis and synthesis formulas. Frequency domain characteristics of linear time invariant system. In this section, we develop the characterization of linear time invariant systems in the frequency domain. The basic excitation signals in this development are the complex exponentials and sinusoidal functions. The characteristics of the system are described by a function of the frequency variable omega called the frequency response, which is the Fourier transform of the impulse response h of n of the system. The frequency response function completely characterizes a linear time invariant system in the frequency domain. This allows us to determine the steady state response of the system to any arbitrary weighted linear combination of sinusoids or complex exponentials. Since periodic sequences in particular lend themselves to a Fourier series decomposition as a weighted sum of harmonically related complex exponentials, it becomes a simple matter to determine the response of a linear time invariant system to this class of signals. This methodology is also applied to aperiodic signals, since such signals can be viewed as a superposition of infinite simul-size complex exponential. Response to complex exponential and sinusoidal signals. The frequency response function. The response of any relaxed linear time invariant system to an arbitrary input signal x of n is given by the convolution sum formula. Y of n equal to summation k equal to minus infinity to plus infinity h of k into x of n minus k. In this input-output relationship, the system is characterized in the time domain by its unit sample response h of n minus infinity less than n less than infinity. To develop a frequency domain characterization of the system, let us excite the system with the complex exponential x of n equal to a into e power j omega n, where minus infinity less than n less than infinity, where a is the amplitude and omega is any arbitrary frequency confined to the frequency interval minus pi comma pi. By substituting previous equation in the first one, we obtain the response y of n equal to summation k equal to minus infinity to plus infinity h of k into a into e power j into omega of n minus k equal to a into summation k equal to minus infinity to plus infinity h of k into e power minus j omega k into e power j omega n. We observe that the term in brackets in this equation is a function of the frequency variable omega. In fact, this term is the Fourier transform of the unit sample response h of k of the system. Hence, we denote this function as h of omega equal to summation k equal to minus infinity to plus infinity h of k into e power minus j omega k. Clearly, the function h of omega exists if the system is BIBO stable, that is, if summation n equal to minus infinity to plus infinity modulus of h of n less than infinity. H of omega equal to summation k equal to minus infinity to plus infinity h of k into e power minus j omega k. For the definition in the response of the system to the complex exponential given in x of n equal to a into e power j omega n minus infinity less than n less than infinity, y of n equal to a into h of omega into e power j omega n. The response is also in the form of a complex exponential with the same frequency as the input, but altered by the multiplicative factor h of omega. The exponential signal in x of n equal to a into e power j omega n minus infinity less than n less than infinity is called an eigenfunction of the system. An eigenfunction of a system is an input signal that produces an output that differs from the input by a constant multiplicative factor. The multiplicative factor is called an eigenvalue of the system. A complex exponential signal of the form is an eigenfunction of a linear time invariant system, and h of omega evaluated at the frequency of the input signal is the corresponding eigenvalue. Example: determine the output sequence of the system with the impulse response h of n equal to 1 by 2 whole power n into u of n, when the input is the complex exponential sequence x of n equal to a into e power j pi n by 2 minus infinity less than n less than infinity. Solution: evaluate the Fourier transform of the impulse response h of n and then use y of n equal to a into h of omega into e power j omega n to determine y of n. H of omega equal to summation n equal to minus infinity to plus infinity h of n e power minus j omega n equal to 1 divided by 1 minus 1 by 2 into e power minus j omega at omega equal to pi by 2. The above equation yields h of pi by 2 equal to 1 divided by 1 plus j into 1 by 2 equal to 2 divided by root 5 into e power minus j into 26.6 degree, and therefore the output is y of n equal to a into 2 divided by root 5 e power minus j 26.6 degree into e power j pi into n by 2. Then y of n equal to 2 divided by root 5 into a into e power j into pi n by 2 minus 26.6 degree, where minus infinity less than n less than infinity. This example illustrates that the only effect of the system on the input signal is to scale the amplitude by 2 divided by root 5 and shift the phase by minus 26.6 degree. Thus the output is also a complex exponential of frequency pi by 2, amplitude 2a divided by root 5 and phase minus 26.6 degree. If we alter the frequency of the input signal, the effect of the system on the input also changes, and hence the output changes. In particular, if the input sequence is a complex exponential of frequency n, that is x of n equal to a into e power I pi n, minus infinity less than n less than infinity, then at omega equal to n, h of pi equal to 1 divided by 1 minus 1 by 2 e power minus j pi equal to 1 divided by 3 by 2 equal to 2 by 3, and the output of the system is y of n equal to 2 by 3 into a into e power j pi n, where minus infinity less than n less than infinity. We note that h of n is purely real, that is, the phase associated with h of omega is 0 at omega equal to n. Hence, the input is scaled in amplitude by the factor h of n equal to 2 by 3, but the phase shift is 0. In general, h of omega is a complex valued function of the frequency variable omega. Hence, it can be expressed in polar form as h of omega equal to modulus of h of omega into e power j into h of omega, where modulus of h of omega is the magnitude of h of omega and capital theta of omega equal to angular point of h of omega, which is the phase shift imparted on the input signal by the system at the frequency omega. Since h of omega is the Fourier transform of modulus of h of k, it follows that h of omega is a periodic function with period 2n. The unit impulse h of k is related to h of omega through the integral expression h of k equal to 1 divided by 2 pi integral minus pi to pi h of omega into e power j omega k into d omega. For a linear time invariant system with a real valued impulse response, the magnitude and phase functions possesses symmetry properties which are developed as follows. From the definition of h of omega, we have h of omega equal to summation k equal to minus infinity to plus infinity h of k into e power minus j omega k equal to summation k equal to minus infinity to plus infinity h of k into cos omega k minus j into summation k equal to minus infinity to plus infinity h of k into sin omega k equal to h r of omega minus j h j of omega equal to square root of hr square of omega minus hj square of omega into e power j tan inverse of h1 of omega plus hr of omega, where hr of omega and h1 of omega denote the real and imaginary components of h of omega, defined as hr of omega equal to summation k equal to minus infinity to plus infinity h of k into cos omega k, h1 of omega equal to minus summation k equal to minus infinity to plus infinity h of k into sin omega k. It is clear that the magnitude and phase of h of omega expressed in terms of hr of omega and h1 of omega are modulus of h of omega equal to square root of hr square of omega plus h1 square of omega. Capital theta of omega equal to tan inverse of h1 of omega divided by hr of omega. We note that hr of omega equal to hr of minus omega and h1 of omega equal to minus h1 of omega, so that hr of omega is an even function of omega and h1 of omega is an odd function of omega. As a consequence, it follows that modulus of h of omega is an even function of omega and capital theta of omega is an odd function of omega. Hence, if we know modulus of h of omega and capital theta of omega for 0 less than or equal to omega less than or equal to n, we also know these functions for minus n less than or equal to omega less than or equal to 0. Example: moving average filter. Determine the magnitude and phase of h of omega for the 3-point moving average system. Y of n equal to 1 by 3 x of n plus 1 plus x of n plus x of n minus 1, and plot these two functions for 0 less than or equal to omega less than or equal to n. Solution: since h of n equal to 1 by 3, 1 by 3, 1 by 3, it follows that h of omega equal to 1 by 3 into e power j omega plus 1 plus e power minus j omega equal to 1 by 3 times of 1 plus 2 into cos omega, where modulus of h of omega equal to 1 by 3 into 1 plus 2 cos omega. Capital theta of omega equal to 0, where 0 less than or equal to omega less than or equal to pi by 3, then pi for 2 pi by 3 less than or equal to omega less than pi. Modulus of h of omega is an even function of frequency and capital theta of omega is an odd function of frequency. It is apparent from the frequency response characteristic h of omega. That is, moving average filter smooths the input data as we would expect from the input-output equation. The symmetry properties satisfied by the magnitude and phase functions of h of omega. Fact that a sinusoid can be expressed as a sum or difference of two complex conjugate exponential functions imply that the response of a linear time invariant system to a sinusoid is similar in form to the response when the input is a complex exponential. Figure magnitude and phase response of a MA system. If the input is x1 of n equal to a into e power j omega n, the output is y1 of n equal to a into modulus of h of omega into e power j into capital theta of omega into e power j omega n. On the other hand, if the input is x2 of n equal to a into e power minus j omega n. The response of the system is y2 of n equal to a into modulus of h of minus omega into e power j into capital theta of minus omega into e power minus j omega n equal to a into modulus of h of omega e power minus j into capital theta of omega into e power minus j omega n, where in the last expression we made use of the symmetry properties modulus of h of omega equal to modulus of h of minus omega and capital theta of omega equal to minus capital theta of omega. Now, by applying the superposition property of the linear time invariant system, we find that the response of the system to the input x of n equal to 1 by 2 into x1 of n minus x2 of n equal to a into cos omega n is y of n equal to 1 by 2 into y1 of n plus y2 of n. Then y of n equal to a into modulus of h of omega into cos omega n plus capital theta of omega. Similarly, if the input is x of n equal to 1 divided by j square into x1 of n minus x2 of n, the response of the system is y of n equal to 1 divided by j square into y1 of n minus y2 of n, then y of n equal to a into modulus of h of omega into sin omega n plus capital theta of omega. H of omega or equivalently modulus of h of omega and capital theta of omega completely characterize the effect of the system on a sinusoidal input signal of any arbitrary frequency. Indeed, modulus of h of omega determines the amplification modulus of h of omega greater than 1 or attenuation modulus of h of omega less than 1 imparted by the system on the input sinusoid. The phase capital theta of omega determines the amount of phase shift imparted by the system on the input sinusoid. By knowing h of omega, we are able to determine the response of the system to any sinusoid input signal. Since h of omega specifies the response of the system in the frequency domain, it is called the frequency response of the system. Correspondingly, modulus of h of omega is called the magnitude response and capital theta of omega is called the phase response of the system. If the input of the system consists of more than one sinusoid, the superposition property of the linear system can be used to determine the response. Steady state and transient response to sinusoid input signals. In the discussion in the preceding section, we determine the response of a linear time invariant system to exponential and sinusoidal input signals applied to the system at n equal to minus infinity. We usually call such signals eternal exponentials or eternal sinusoid because they were applied at n equal to minus infinity. In such a case, the response that we observe at the output of the system is the steady state response. There is no transient response in this case. On the other hand, if the exponential or sinusoidal signal is applied at some infinite time instant, say at n equal to 0. The response of the system consists of two terms, the transient response and the steady state response. To demonstrate this behavior, let us consider as an example the system described by the first order difference equation y of n equal to a into y of n minus 1 plus x of n. Its response to any input x of n applied at n equal to 0 is given by y of n equal to a power n plus 1 into y of minus 1 plus summation k equal to 0 to n a power k into x of n minus k, where n greater than or equal to 0, where y of minus 1 is the initial condition. Now let us assume that the input to the system is the complex exponential x of n equal to a into e power j omega n, where n greater than or equal to 0. Applied at n equal to 0, we obtain y of n equal to a power n plus 1 into y of minus 1 plus a into summation k equal to 0 to n a power k into e power j into omega of n minus k equal to a power n plus 1 into y of minus 1 plus a into summation k equal to 0 to n a into e power minus j omega whole power k into e power j omega n equal to a power n plus 1 into y of minus 1 plus a into 1 minus a power n plus 1 into e power minus j omega of n plus 1 divided by 1 minus a into e power minus j omega into e power j omega n, where n greater than or equal to 0, equal to a power n plus 1 into y of minus 1 minus a into a power n plus 1 into e power minus j omega into omega of n plus 1 divided by 1 minus a into e power minus j omega into e power j omega n plus a divided by 1 minus a into e power minus j omega into e power j omega n, where n greater than or equal to 0. System is BIBO stable if modulus of a less than 1. In this case, the two terms involving a power n plus 1 decay towards 0 as n approaches infinity. Consequently, we are left with the steady state response YSS of n equal to limit n tends to infinity y of n equal to a divided by 1 minus a into e power minus j omega into e power j omega n equal to a into h of omega into e power j omega n. The first two terms constitute the transient response of the system, that is ytt of n equal to a power n plus 1 into y of minus 1 minus a into a power n plus 1 into e power minus j omega of n plus 1 divided by 1 minus a into e power minus j omega into e power j omega n, where n greater than or equal to 0, which decay toward 0 as n approaches infinity. The first term in the transient response is the zero input response of the system, and the second term is the transient produced by exponential input signal. In general, all linear time invariant BIBO systems behave in a similar fashion. when excited by a complex exponential or by a sinusoid at n equal to 0 or at some other finite time instant. The transient response decays towards 0 as n tends to infinity, leaving only the steady state response that we determined in the preceding section. In many practical applications, the transient response of the system is unimportant and therefore it is usually ignored in dealing with the response of the system to sinusoidal inputs. Steady state response to periodic input signals. Suppose that the input to a stable linear time invariant system is a periodic signal x of n with fundamental period n. Since such a signal exists from minus infinity less than n less than infinity, the total response of the system at any time instant n is simply equal to the steady state response. To determine the response y of n of the system, we make use of the Fourier series representation of the periodic signal, which is x of n equal to summation k equal to 0 to n minus 1 ck into e power j 2k n by n, at k equal to 0, 1, etc. n minus 1, where the ck or the Fourier series coefficient of the response of the system to the complex exponential signal xk of n equal to ck into e power j 2 pi k n by n, where k equal to 0, 1, etc. n minus 1 is yk of n equal to ck into h of 2 pi by n into k into e power j 2 pi k n by n, where k equal to 0, 1, etc. capital N minus 1, where h of 2 pi k by n equal to h of omega, where k equal to 0, 1, etc. n minus 1. By using the superposition principle for linear systems, we obtain the response of the system to the periodic signal x of n as y of n equal to summation k equal to 0 to n minus 1 ck into h of 2 pi k divided by n into e power j 2 pi k n by n, where minus infinity less than n less than infinity. This result implies that the response of the system to the periodic input signal x of n is also periodic with the same period n. The Fourier series coefficient for y of n are dk equivalent to ck into h of 2 pi k divided by n, where k equal to 0, 1, etc. n minus 1. Hence, the linear system can change the shape of the periodic input signal by scaling the amplitude and shifting the phase of the Fourier series components, but it does not affect the period of the periodic input signal. Response to aperiodic input signals. The convolution theorem provides the desired frequency domain relationship for determining the output of an LTI system to an aperiodic finite energy signal. If x of n denotes the input sequence, y of n denotes the output sequence, and h of n denotes the unit sample response of the system, then from the convolution theorem we have y of omega equal to h of omega into x of omega, where y of omega, x of omega and h of omega are the corresponding Fourier transforms of y of n, x of n and h of n respectively. From this relationship, we observe that the spectrum of the output signal is equal to the spectrum of the input signal multiplied by the frequency response of the system. If we express y of omega, h of omega and x of omega in polar form, the magnitude and phase of the output signal can be expressed as modulus of y of omega equal to modulus of h of omega into modulus of x of omega. Angular point of y of omega equal to angular point of x of omega plus angular point of h of omega, where modulus of h of omega and LH of omega are the magnitude and phase responses of the system. By its very nature, a finite energy aperiodic signal contains a continuum of frequency components. The linear time invariant system, through its frequency response function, attenuates some frequency components of the input signal and amplifies other frequency components. The system acts as a filter to the input signal. Observation of the graph of modulus of h of omega shows which frequency components are amplified and which are attenuated. The angle of h of omega determines the phase shift imparted in the continuum of the frequency components of the input signal as a function of frequency. If the input signal spectrum is changed by the system in an undesirable way, the system has caused magnitude and phase distortion. The output of a linear time invariant system cannot contain frequency components that are not contained in the input signal. It takes either a linear time variant system or a non-linear system to create frequency components that are not necessarily contained in the input signal. The time domain and frequency domain relationships that can be used in the analysis of BI/BO stable LTA systems. In time domain analysis, we deal with the convolution of the input signal with the impulse response of the system to obtain the output sequence of the system. On the other hand, in frequency domain analysis, we deal with the input signal spectrum x of omega and the frequency response h of omega of the system, which are related through multiplication to yield the spectrum of the signal at the output of the system. The output sequence y of n can be determined from the inverse Fourier transform. Y of n equal to 1 by 2 pi integral minus pi to pi y of omega into e power j omega n into d omega. However, this method is seldom used. Instead, the Z transform is a simpler method for solving the problem of determining the output sequence y of n. Let us return to the basic input-output relation and compute the standard magnitude of both sides. Thus, we obtain modulus of y of omega the whole square equal to modulus of h of omega the whole square into modulus of x of omega the whole square. Then s y of omega equal to modulus of h of omega the whole square into s xx of omega, where s xx of omega and s y of omega are the energy density spectra of the input and output signals respectively. By integrating over the frequency range minus n, n, we obtain the energy of the input signal as Ey equal to 1 by 2 pi integral minus phi to pi s y of omega into d omega equal to 1 by 2 pi integral minus pi to pi modulus of h of omega the whole square into s x of omega into d omega. Example: a linear time invariant system is characterized by its impulse response h of n equal to 1 by 2 the whole power n into u of n. Determine the spectrum and the energy density spectrum of the output signal when the system is excited by the signal x of n equal to 1 by 4 the whole power n into u of n. Solution: the frequency response function of the system h of omega equal to summation n equal to 0 to infinity 1 by 2 the whole power n into e power minus j omega n equal to 1 divided by 1 minus 1 by 2 into e power minus j omega. Similarly, the input sequence x of n as a Fourier transform x of omega equal to 1 divided by 1 minus 1 by 4 into e power minus j omega. Hence, the spectrum of the signal at the output of the system is y of omega equal to h of omega into x of omega equal to 1 divided by 1 minus 1 by 2 into e power minus j omega into 1 minus 1 by 4 into e power minus j omega. The corresponding energy density spectrum is S xx of omega equal to y of omega the whole square equal to modulus of h of omega the whole square into modulus of x of omega the whole square equal to 1 divided by 5 by 4 minus cos omega into 17 by 16 minus 1 by 2 into cos omega. Relationships between the system function and the frequency response function. If the system function h of z converges on the unit circle, we can obtain the frequency response of the system by evaluating h of z on the unit circle. Thus, h of omega equal to h of z at z equal to e power j omega equal to summation n equal to minus infinity to plus infinity h of n into e power minus j omega n. In the case where h of z is a rational function, the form h of z equal to b of z divided by a of z. We have h of omega equal to b of omega divided by a of omega equal to summation k equal to 0 to m bk into e power minus j omega k divided by 1 plus summation k equal to 1 to n ak into e power minus j omega k equal to b naught into pi k equal to 1 to m 1 minus zk into e power minus j omega divided by pi k equal to 1 to n 1 minus pk into e power minus j omega, where the ak and bk are real but zk and pk may be complex valued. It is sometimes desirable to express the magnitude squared of h of omega in terms of h of z. First, note that modulus of h of omega the whole square equal to h of omega into h star of omega. For the rational system function, we have h star of omega equal to b naught into pi k equal to 1 to m 1 minus zk star into e power j omega divided by pi k equal to 1 to n 1 minus pk star into e power j omega. It follows that h star of omega is obtained by evaluating h star of 1 by z star on the unit circle for a rational system function, h star of 1 by z star equal to b naught into pi k equal to 1 to m 1 minus zk star into z divided by pi k equal to 1 to n 1 minus pk star into z. However, when h of n is real or equivalently, the coefficients ak and bk are real, complex valued poles and zeros occur in complex conjugate pairs. In this case, h star of 1 by z star equal to h of z inverse. Consequently, h star of omega equal to h of minus omega and modulus of h of omega the whole square equal to h of omega into h star of omega equal to h of omega into h of minus omega equal to h of z into h of z inverse at z equal to e power j omega. According to the correlation theorem for the z transform, the function h of z into h of z inverse is the z transform of the autocorrelation sequence or h of m of the unit sample response h of n. Then it follows from the Wiener-Khinchin theorem that modulus of h of omega the whole square is the Fourier transform of or h of m. If h of z equal to b of z divided by a of z, the transforms d of z equal to b of z into b of z inverse and c of z equal to a of z into a of z inverse or the z transforms of the autocorrelation sequences C1 and D1, where Cl equal to summation k equal to 0 to n minus modulus of L ak into ak plus 1, where minus n less than or equal to L less than or equal to n. Then dl equal to summation k equal to 0 to m minus modulus of L bk into bk plus 1, where minus m less than or equal to L less than or equal to m. Since the system parameters ak and bk are real valued, it follows that C1 equal to C minus 1 and D1 equal to D minus 1 by using the symmetry property. Modulus of h of omega the whole square may be expressed as modulus of h of omega the whole square equal to d naught plus 2 times of summation k equal to 1 to m dk into cos k omega divided by c naught plus 2 times of summation k equal to 1 to n ck into cos k omega. Finally, we note that cos k omega can be expressed as a polynomial function of cos omega, that is cos k omega equal to summation m equal to 0 to k beta m into cos omega the whole power m, where beta m are the coefficients in the expansion. Consequently, the numerator and denominator of modulus of h of omega the whole square can be viewed as polynomial functions of cos omega. Example: determine modulus of h of omega the whole square for the system y of n equal to minus 0.1 into y of n minus 1 plus 0.2 into y of n minus 2 plus x of n plus x of n minus 1. Solution: the system function is h of z equal to 1 plus z inverse divided by 1 plus 0.1 into z inverse minus 0.2 into z power minus 2, and its ROC is modulus of z greater than 0.5. Hence, h of omega exists. Now, h of z into h of z power minus 1 equal to 1 plus z power minus 1 divided by 1 plus 0.1 into z power minus 1 minus 0.2 into z power minus 2 into 1 plus z divided by 1 plus 0.1 into z minus 0.2 into z square. equal to 2 plus z power minus 1 divided by 1.05 plus 0.08 into z plus z power minus 1 minus 0.2 into z power minus 2 plus z power minus 2. By evaluating h of z into h of z power minus 1 on the unit circle, we obtain modulus of h of omega the whole square equal to 2 plus 2 cos omega divided by 1.05 minus 0.16 into cos omega minus 0.4 into cos 2 omega. However, cos 2 omega equal to 2 cos square omega minus 1. Consequently, modulus of h of omega the whole square may be expressed as modulus of h of omega the whole square equal to 2 times of 1 plus cos omega divided by 1.45 plus 0.16 into cos omega minus 0.8 into cos square omega. We note that given h of z, it is straightforward to determine h of z power minus 1 and then modulus of h of omega the whole square. However, the inverse problem of determining h of z given modulus of h of omega the whole square or the corresponding impulse response h of n is not straightforward, since modulus of h of omega the whole square does not contain the phase information in h of omega. It is not possible to uniquely determine h of z. Computation of the frequency response function. In evaluating the magnitude response and the phase response as functions of frequency, it is convenient to express h of omega in terms of its poles and zeros. Hence, we write h of omega in factored form as h of omega equal to b naught into pi k equal to 1 to m 1 minus zk into e power minus j omega k divided by pi k equal to 1 to n 1 minus pk into e power minus j omega k, or equivalently as h of omega equal to b naught into e power j omega into n minus m into pi k equal to 1 to m e power j omega minus zk divided by pi k equal to 1 to n e power j omega minus pk. Let us express the complex valued factors in 4.47 in polar form as e power j omega minus zk equal to vk of omega into e power j theta k of omega, and e power j omega minus pk equal to uk of omega into e power j pi k of omega, where vk of omega equivalent to modulus of e power j omega minus zk, capital theta k of omega equivalent to angle of e power j omega minus zk, and uk of omega equivalent to modulus of e power j omega minus pk, pi k of omega equal to angular of e power j omega minus pk. The magnitude of h of omega is equal to the product of magnitudes of all terms. Thus, modulus of h of omega equal to modulus of b naught into v1 of omega etc. till vm of omega divided by u1 of omega into u2 of omega etc. un of omega, since the magnitude of e power j omega into n minus m is 1. The phase of h of omega is the sum of the phases of the numerator factors minus the phases of the denominator factors. Angle of h of omega equal to angle of b naught plus omega of n minus m plus capital theta 1 of omega plus capital theta 2 of omega plus etc. plus capital theta m of omega. minus pi 1 of omega plus pi 2 of omega etc. plus pi n of omega. The phase of the gain term B naught is 0 or n depending on whether B naught is positive or negative. Clearly, if we know the zeros and the poles of the system function h of z, we can evaluate the frequency response. Let us consider a pole pk and a zero zk located at points A and B of the z plane. Assume that we wish to compute h of omega at a specific value of frequency omega. The given value of omega determines the angle of e power j omega with the positive real axis. The tip of the vector e power j omega specifies a point L on the unit circle. The evaluation of the Fourier transform for the given value of omega is equivalent to evaluating the z transform at point L of the complex plane. Let us draw the vectors AL and BL from the pole and 0 locations to the point L at which we wish to compute the Fourier transform CL equal to CA plus AL and CL equal to CB plus BL. However, CL equal to e power j omega, CA equal to pk and CB equal to zk. Thus, AL equal to e power j omega minus pk and BL equal to e power j omega minus zk. Unit circle z equal to e power j omega or modulus of z equal to 1. Unit circle. By combining these relations, we obtain AL equal to e power j omega minus pk equal to uk of omega into e power j pi k of omega. BL equal to e power j omega minus zk equal to vk of omega into e power j capital theta k of omega. This uk of omega is the length of AL, that is the distance of the pole pk from the point L corresponding to e power j omega, whereas vk of omega is the distance of the 0 zk from the same point L. The phases vk of omega and capital theta k of omega are the angles of the vectors AL and BL. The presence of a zero close to the unit circle causes the magnitude of the frequency response at frequencies that correspond to points of the unit circle causes the magnitude of the frequency response to be large at frequencies close to that point. The poles have the opposite effect of zeros. Also, placing a zero close to a pole cancels the effect of the pole and vice versa. The presence of both poles and zeros in a transform results in a greater variety of shapes for modulus of h of omega and angle of h of omega. Example: evaluate the frequency response of the system described by the system function h of z equal to 1 divided by 1 minus 0.8 into z inverse equal to z divided by z minus 0.8. Solution: clearly h of z as a 0 at z equal to 0 and a pole at p equal to 0.8. Hence, the frequency response of the system is h of omega equal to e power j omega divided by e power j omega minus 0.8. The magnitude response is modulus of h of omega equal to modulus of e power j omega divided by modulus of e power j omega minus 0.8 equal to 1 divided by square root of 1.64 minus 1.6 into cos omega. And the phase responses h of omega equal to omega minus tan inverse of sin omega divided by cos omega minus 0.8. The peak of the magnitude response occurs at omega equal to 0, the point on the unit circle closest to the pole located at 0.8. If the magnitude response is expressed in decibels, modulus of h of omega equal to 20 into log base 10 modulus of b naught plus 20 into summation k equal to 1 to m log base 10 vk of omega minus 20 into summation k equal to 1 to n log base 10 uk of omega. Thus, the magnitude response is expressed as a sum of the magnitude factors in modulus of h of omega. Input-output correlation functions and spectra. We derived the following equations in correlation relationships between the input and the output sequences of an LTI system. Or yy of m equal to or hh of m into or xx of m, or yx of m equal to h of m into or xx of m, where or xx of m is the autocorrelation sequence of the input signal x of n, or yy of m is the autocorrelation sequence of the output y of n, or hh of m is the autocorrelation sequence of the impulse response h of n, and or yx of m is the cross correlation sequence between the output and input signals. Since above equations involve the convolution operation, the Z transform of these equations yields Syy of Z equal to Shh of Z into Sz of Z equal to h of Z into h of Z power minus 1 into Sxx of Z. Syx of Z equal to h of Z into Sxx of Z. If we substitute Z equal to e power j omega, we obtain Syx of omega equal to h of omega into Sxx of omega equal to h of omega into modulus of x of omega the whole square, where Syx of omega is the cross energy density spectrum of y of n and x of n. Similarly, evaluating Syy of Z on the unit circle yields the energy density spectrum of the output signal as Syy of omega equal to modulus of h of omega the whole square into Sxx of omega, where Sxx of omega is the energy density spectrum of the input signal. Since Ryy of m and Syy of omega are a Fourier transform pair, it follows that Ryy of m equal to 1 by 2 pi integral minus pi to pi Syy of omega e power j omega m d omega. The total energy in the output signal is simply Ey equal to 1 by 2 pi integral minus pi to pi Syy of omega into d omega equal to Ryy of 0 equal to 1 by 2 pi integral minus pi to pi modulus of h of omega the whole square into Sxx of omega into d omega. The result proves that Ey greater than or equal to 0. If the input signal has a flat spectrum, that is Sxx of omega equal to Ex equal to constant for n less than or equal to omega less than or equal to minus n, Sxx of omega reduces to Syx of omega equal to h of omega into Ex, where Ex is the constant value of the spectrum. Hence, h of omega equal to 1 by ex into s yx of omega, or equivalently h of n equal to 1 by ex into or yx of m. The relation implies that h of n can be determined by exciting the input to the system by a spectrally flat signal x of n and cross correlating the input with the output of the system. This method is useful in measuring the impulse response of an unknown system. Figure: magnitude and phase of system with h of z equal to 1 divided by 1 minus 0.8 into z power minus 1. Correlation functions and power spectra for random input signal. We now deal with statistical moments of the input and output signals of an LTI system. Let us consider a discrete time linear time invariant system with unit sample response h of n and frequency response h of f. For this development, we assume that h of n is real. Let x of n be a function of a stationary random process x of n that excites the system, and let y of n denote the response of the system to x of n. From the convolution summation that relates the output to the input, we have y of n equal to summation k equal to minus infinity to plus infinity h of k into x of n minus k. Since x of n is a random input signal, the output is also a random sequence. For each sample sequence x of n of the process x of n, there is a corresponding sample sequence y of n of the output random process y of n to the statistical characterization of the input process and the characteristics of the system. The expected value of the output y of n is my equivalent to expectation of y of n equal to expectation of summation k equal to minus infinity to plus infinity h of k into x of n minus k equal to summation k equal to minus infinity to plus infinity h of k into expectation of x of n minus k. Then my equal to mx into summation k equal to minus infinity to plus infinity h of k. From the Fourier transform relationship, h of omega equal to summation k equal to minus infinity to plus infinity h of k into e power minus j omega k, we have h of 0 equal to summation k equal to minus infinity to plus infinity h of k, whereas the DC gain of the system. From our relationship, we express the mean value as my equal to mx into h of 0. The autocorrelation sequence for the output random processes y of m equal to expectation of y star of n into y of n plus m equal to expectation of summation k equal to minus infinity to plus infinity h of k into x star of n minus k into summation j equal to minus infinity to plus infinity h of j into x of n plus m minus j equal to summation k equal to minus infinity to plus infinity into summation j equal to minus infinity to plus infinity h of k into h of j into expectation of x star of n minus k into x of n plus m minus j equal to summation k equal to minus infinity to plus infinity into summation j equal to minus infinity to plus infinity h of k into h of j into yxx of k minus j plus m. This is the general form for the autocorrelation of the output in terms of the autocorrelation of the input and the impulse response of the system. A special form is obtained when the input random process is void, that is, when mx equal to 0 and gamma xx of m equal to sigma x square delta of m, where sigma x square equal to gamma xx of 0 is the input signal power, then 4.4.75 reduces to gamma yy of m equal to sigma x square into summation k equal to minus infinity to plus infinity h of k into h of k plus m. Under this condition, the output process has the average power. Gamma yy of 0 equal to sigma x square into summation n equal to minus infinity to plus infinity h square of n equal to sigma x square integral minus 1 by 2 to plus 1 by 2 modulus of h of f the whole square into df, where we have applied Percival's theorem. The autocorrelation sequence for the output random process can be transformed into the frequency domain by determining the power density spectrum of gamma yy of m. Gamma yy of omega equal to summation m equal to minus infinity to plus infinity gamma yy of m into e power minus j omega m equal to summation m equal to minus infinity to plus infinity into summation k equal to minus infinity to plus infinity into summation L equal to minus infinity to plus infinity h of k into h of L into gamma xx of k minus L plus m into e power minus j omega n equal to summation k equal to minus infinity to plus infinity into summation L equal to minus infinity to plus infinity h of k into h of L into summation m equal to minus infinity to plus infinity gamma xx of k minus L plus m into e power minus j omega m equal to gamma xx of f into summation k equal to minus infinity to plus infinity h of k into e power j omega k into summation L equal to minus infinity to plus infinity h of L into e power minus j omega L equal to modulus of h of omega the whole square into gamma xx of omega. This is the desired relationship for the power density spectrum of the output process in terms of the power density spectrum of the input process and the frequency response of the system. The equivalent expression for continuous time systems with the random inputs is gamma yy of f equal to modulus of h of f the whole square into gamma xx of f, where the power density spectra gamma yy of f and gamma xx of f are the Fourier transforms of the autocorrelation functions gamma yy of t and gamma xx of t respectively, and h of f is the frequency response of the system, which is related to the impulse response by the Fourier transform, that is h of f equal to integral minus infinity to plus infinity h of t into e power minus j 2 pi ft into dt. As a final exercise, we determine the cross correlation of the output y of n with the input signal x of n if we multiply both sides of convolution summation by x star of n minus m and take expected value we obtain. Expectation of y of n into x star of n minus m equal to expectation of summation k equal to minus infinity to plus infinity h of k into x star of n minus m into x of n minus k. Gamma yx of m equal to summation k equal to minus infinity to plus infinity h of k into expectation of x star of n minus m into x of n minus k equal to summation k equal to minus infinity to plus infinity h of k into gamma xx of m minus k. Since above equation has the form of a convolution, the frequency domain equivalent expression is gamma yx of omega equal to h of omega into gamma xx of omega. In the special case where x of n is white noise, gamma yx of omega equal to sigma x square into h of omega, where sigma x square is the input noise power. An unknown system with frequency response h of omega can be identified by exciting the input with white noise, cross correlating the input sequence with the output sequence to obtain gamma yx of m, and finally computing the Fourier transform gamma yx of m. Frequency analysis of continuous time signals. Frequency analysis of signals and systems. The Fourier transform is one of several mathematical tools that is useful in analysis and design of LTE systems. Another is Fourier series. These signal representations basically involve the decomposition of the signals in terms of sinusoidal components. With such a decomposition, a signal is said to be represented in the frequency domain. Most signals of practical interest can be decomposed into a sum of sinusoidal signal components. For the class of periodic signals, the decomposition is called the Fourier series. For the class of finite energy signals, the decomposition is called the Fourier transform. We begin our study of frequency analysis of signals with the representation of continuous time periodic and aperiodic signals by means of the Fourier series and the Fourier transform. Topics discussed in this chapter: frequency analysis, continuous time signals, Fourier series for continuous time period signals, power density spectrum of periodic signals, the Fourier transform for continuous time aperiodic signal, energy density spectrum of aperiodic signals, frequency analysis discrete time signals, Fourier series for discrete time period signals, power density spectrum of periodic signals, the Fourier transform for discrete time aperiodic signal, energy density spectrum of aperiodic signals, relationship of the Fourier transform to the Z transform, the spectrum, the Fourier transform of signals with poles on the unit circle, the sampling theorem revisited, frequency domain classification of signals, the concept of bandwidth, the frequency ranges of some natural signals, physical and mathematical dualities. Properties of the Fourier transform for discrete time signals. Symmetry properties of the Fourier transform, Fourier transform theorems and properties, frequency domain characteristics of LTE systems, response to complex exponential and sinusoidal signals, the frequency response function, steady state and transient response to sinusoidal input signals, steady state response to periodic input signals, response to aperiodic input signals, relationships between the system function and the frequency response function, computation of the frequency response function, input-output correlation functions and spectra, correlation functions and power spectra for random input signals. LTE system has a frequency selective filter. Ideal filter characteristics: low pass, high pass and band pass filters, digital resonators, notch filters, comb filters, all-pass filters, digital sinusoidal oscillators, inverse systems and deconvolution, invertibility of linear time invariant systems, minimum phase, maximum phase and mixed phase systems, system identification and deconvolution, homomorphic deconvolution. The process of obtaining the spectrum of a given signal using the basic mathematical tools is known as frequency or spectral analysis. The process of determining the spectrum of a signal in practice based on actual measurements of the signal is called spectrum estimation. The term spectrum is used when referring to a frequency content of a signal. The information contained in a signal can be extracted directly or indirectly from the Fourier series for continuous time periodic signals. In this section, let us see the frequency analysis tools for continuous time periodic signals. Example of periodic signals are square waves, rectangular waves, triangular waves, sinusoids and complex exponential. The basic mathematical representation of periodic signals is the Fourier series, which is a linear weighted sum of harmonically related sinusoids or complex exponential. The linear combination of harmonically related complex exponential of the form x of t equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f naught t is a periodic signal with fundamental period Tp equal to 1 divided by f naught. Hence, the exponential signals is e power j 2 pi k f naught t, where k equal to 0, plus or minus 1, plus or minus 2, etc. The basic building blocks from which we can construct periodic signals of various types of proper choice of the fundamental frequency and the coefficients Ck. F naught determines the fundamental period of x of t and the coefficients Ck specify the shape of the waveform. Multiply both sides of the complex exponential e power minus j 2 pi L f naught t, where L is an integer, and then integrate both sides of the resulting equation over a signal period, say from 0 to Tp or from T0 to T0 plus Tp, where R0 is an arbitrary but mathematically convenient starting values. Thus, integral limit T0 to T0 plus Tp x of t into e power minus j 2 pi L f naught t into dt equal to integral T0 to T0 plus Tp e power minus j 2 pi L f naught t into within the bracket summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f naught t into dt. Interchange the order of summation and integration and combine the two exponentials. Hence, summation k equal to minus infinity to plus infinity ck integral T0 to T0 plus Tp e power j 2 pi f naught into k minus L into t into dt equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi f naught into k minus L into t divided by j 2 pi f naught into k minus L with the limit T0 to T0 plus Tp. We getting this after integrating. For k not equal to 1, the right hand side is evaluated at the lower and upper limits T0 and T0 plus Tp respectively yields 0. On other hand, if k equal to 1, we have integral T0 to T0 plus Tp into dt equal to t with the limit T0 to T0 plus Tp equal to Tp. Consequently, integral T0 to T0 plus Tp x of t into e power minus j 2 pi L f naught into t into dt equal to CL into Tp, and therefore the expression for the Fourier coefficients in term of the given periodic signal becomes CL equal to 1 divided by Tp integral T0 to T0 plus Tp x of t into e power minus j 2 pi L f naught into t into dt. Since T0 is arbitrary, this integral can be evaluated over any interval of length Tp, that is over any interval equal to the period of the signal x of t. Consequently, the integral for the Fourier series coefficients will be written as CL equal to 1 divided by Tp integral under Tp x of t into e power minus j 2 pi L f naught into t into dt. An important issue that arises in the representation of the periodic signal x of t by the Fourier series is whether or not the series converges to x of t for every value of t, that is, if the signal x of t and its Fourier series representation summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f naught into t are equal at every value of t. The so-called Dirichlet conditions guarantee that the series will be equal to x of t except at the values of t for which x of t is discontinuous. The Dirichlet conditions are: the signal x of t has a finite number of discontinuous in any period. The signal x of t contains a finite number of maxima and minima during any period. The signal x of t is absolutely integrable in any period, that is, integral limit Tp modulus of x of t into dt less than infinity. All periodic signals of interest satisfy these conditions. The weaker condition that the signal has finite energy in one period. Integral limit Tp modulus of x of t the whole square into dt less than infinity guarantees that the energy in the different signal e of t equal to x of t minus summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f naught into t is 0, although x of t and its Fourier series may not be equal for all values of t. Frequency analysis of continuous time periodic signals. Synthesis equation: x of t equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f naught into t. Analysis equation: ck equal to 1 divided by Tp integral Tp x of t into e power minus j 2 pi k f naught into t into dt. The Fourier coefficients ck are complex valued if the periodic signal is real. Ck and ck are complex conjugates if ck equal to modulus of ck e power j theta k, then c minus k equal to modulus of ck minus j theta k. Consequently, the Fourier series may also be represented in the form x of t equal to c naught plus 2 into summation k equal to 1 to infinity modulus of ck into cos of 2 pi k f naught t plus theta k, where c naught is real valued when x of t is real. Another form of indicating the Fourier series is obtained by expanding the cosine function as cos of 2 pi k f naught into t plus theta k equal to cos 2k pi f naught t cos theta k minus sin 2k pi f naught t sin theta k. We can write above equation as x of t equal to a naught plus summation k equal to 1 to infinity ak cos 2 pi k f naught t minus bk sin 2k pi f naught t. where A naught equal to C naught, AK equal to 2 into modulus of CK cos theta k, BK equal to 2 into modulus of CK sin theta k. Power density spectrum of periodic signals. A periodic signal has infinite energy and a finite average power, which is given as Px equal to 1 divided by Tp integral under limit Tp modulus of x of t the whole square into dt. If we take complex conjugate of the synthesis equation and substitute for x star of t, Px equal to 1 divided by Tp integral limit Tp x of t into summation k equal to minus infinity to plus infinity Ck star e power minus j 2 pi k f naught t into dt equal to summation k equal to minus infinity to plus infinity Ck star into 1 divided by Tp integral Tp x of t into e power minus j 2 pi k f naught t into dt equal to summation k equal to minus infinity to plus infinity modulus of Ck square. Therefore, we have established the relation Px equal to 1 divided by Tp integral limit Tp modulus of x of t the whole square into dt equal to summation k equal to minus infinity to plus infinity modulus of Ck the whole square, which is called Parseval's relation for power signals. Power density spectrum of a continuous time periodic signal. The average power in the signal is Px equal to modulus of Ck the whole square. Modulus of Ck the whole square represents the power in the kth harmonic component of the signal. The total average power in the periodic signal is simply the sum of the average powers in all the harmonics. If we plot the modulus of Ck the whole square as a function of the frequencies k into f naught, where k equal to 0, plus or minus 1, plus or minus 2, etc. The diagram we obtain shows how the power of the periodic signal is distributed among the various frequency components. This diagram is called the power density spectrum. Since the power in a periodic signal exists only at the discrete values of frequencies, that is f equal to 0, plus or minus f naught, plus or minus 2 f naught, etc. The signal is said to have a line spectrum. The spacing between two consecutive spectral lines is equal to the reciprocal of the fundamental period Tp, whereas the shape of the spectrum depends on the time domain characteristics of the signal. The Fourier series coefficients Ck or complex values represented as Ck equal to modulus of Ck e power j theta k, where theta k is the angle at the point Ck. If the periodic signal is real valued, the Fourier coefficient Ck satisfies the condition Ck equal to Ck star. Consequently, modulus of Ck square equal to modulus of Ck star the whole square. Power spectrum is a symmetric function of frequency. The magnitude spectrum is symmetric even function about the origin, and the phase spectrum is an odd function. As a consequence of the symmetry, it is sufficient to specify the spectrum of real periodic signal for positive frequencies only. The total average power can be expressed as Px equal to C naught square plus 2 times of summation k equal to 1 to infinity modulus of Ck the whole square equal to A naught square plus 1 by 2 into summation k equal to 1 to infinity ak square plus bk square. The Fourier transform for continuous time aperiodic signals. If we allow period to increase without limit, the line spacing tends towards 0. If the limit when the period becomes infinite, the signal becomes aperiodic and its spectrum becomes continuous. The spectrum of an aperiodic signal will be the envelope of the line spectrum in the corresponding periodic signal obtained while repeating the aperiodic signal with some period Tp. Figure A. Aperiodic signal x of t, and B. Periodic signal xp of t constructed by repeating x of t with the period Tp. Consider an periodic signal x of t with the finite duration as shown in above figure. From this aperiodic signal, we can create a periodic signal xp of t with the period Tp. Clearly, xp of t equal to x of t in the limit Tp tends to infinity, that is, x of t equal to limit Tp tends to infinity xp of t. The Fourier series representation of xp of t equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi I k f naught t, where f naught equal to 1 divided by Tp, where ck equal to 1 divided by Tp integral limit minus Tp by 2 to Tp by 2 xp of t into e power minus j 2 pi k f naught t into dt. Since xp of t equal to x of t for minus Tp by 2 less than or equal to t less than or equal to Tp by 2 can be expressed as ck equal to 1 divided by Tp integral with limit minus Tp by 2 to Tp by 2 x of t into e power minus j 2 pi k f naught t into dt. X of t equal to 0 for modulus of t greater than Tp by 2. The limits on the integral can be replaced by minus infinity and plus infinity. Hence, ck equal to 1 divided by Tp integral minus infinity to plus infinity x of t into e power minus j 2 pi k f naught t into dt. Let us now define a function x of f called the Fourier transform of x of t as x of f equal to integral minus infinity to plus infinity x of t into e power minus j 2 pi f t into dt. The Fourier coefficients can be expressed as ck equal to 1 divided by Tp x of kf naught, or Tp ck equal to x of kf naught equal to x of k divided by Tp. Thus, the Fourier coefficients or samples of x of f taken at multiples of f naught and scaled by f naught multiplied by 1 divided by t naught. Substituting ck from above equation into the Fourier representation xp of t, we get xp of t equal to 1 divided by Tp summation k equal to minus infinity to plus infinity x of k divided by Tp e power j 2 pi k f naught t. We define delta f equal to 1 divided by Tp and substitute in above equation xp of t equal to summation k equal to minus infinity to plus infinity x of k delta f e power j 2 pi k delta f t into delta f. As Tp approaches infinity, xp of t reduces to x of t. Delta f becomes the difference df and k delta f becomes the continuous frequency variable f. Summation becomes an integral over the frequency variable f. Thus, limit Tp tends to infinity xp of t equal to x of t equal to limit delta f tends to 0 summation k equal to minus infinity to plus infinity x of k delta f e power j 2 pi k delta f t into delta f. X of t equal to integral minus infinity to plus infinity x of f into e power minus 2 pi f t into df. Integral yields x of t and x of f is known. This is called the inverse Fourier transform. Frequency analysis of continuous time aperiodic signals. Synthesis equation inverse transform. X of t equal to integral minus infinity to plus infinity x of f into e power j 2 pi ft into df. Analysis equation direct transform. X of f equal to integral minus infinity to plus infinity x of t into e power minus j 2 pi I ft into dt. The Fourier transform pair can be expressed in terms of radian frequency variable omega equal to 2 pi f, since df equal to d omega by 2 pi. X of t equal to 1 divided by 2 pi integral minus infinity to plus infinity x of omega e power minus j omega t into d omega. X of omega equal to integral minus infinity to plus infinity x of t into e power minus j omega t into dt. The set of conditions that guarantee the existence of the Fourier transform is the Dirichlet conditions. The signal x of t has a finite number of finite discontinuities. Number 2, the signal x of t has a finite number of maxima and minima. Number 3, the signal x of t is absolutely integrable, that is, integral minus infinity to plus infinity modulus of x of t into dt less than infinity. The third condition of Dirichlet condition follows from the analysis equation direct transform of the Fourier transform. Modulus of x of f equal to modulus of integral minus infinity to plus infinity x of t into e power minus j 2 pi ft into dt less than or equal to integral minus infinity to plus infinity modulus of x of t into dt. Hence, modulus of x of f less than infinity if the third condition of Dirichlet condition is satisfied. A weaker condition for the existence of the Fourier transform is that x of t has finite energy. Integral minus infinity to plus infinity modulus of x of t the whole square into dt less than infinity. If a signal x of t is absolutely integrable, it will also have finite energy. Integral minus infinity to plus infinity modulus of x of t into dt less than infinity. Then Ex equal to integral minus infinity to plus infinity modulus of x of t the whole square into dt less than infinity. However, the converse is not true. A signal may have a finite energy but may not be absolutely integrable. For example, the signal x of t equal to sine 2 pi t divided by pi t is a square integrable but is not absolutely integrable. The signal has the Fourier transform x of f equal to 1 for modulus of f less than or equal to 1 and 0 for modulus of f greater than 1. Energy density spectrum of aperiodic signals. Let x of t be any finite energy signal with Fourier transform x of f. Its energy is Ex equal to integral minus infinity to plus infinity modulus of t the whole square into dt, which in turn may be expressed in terms of x of f as follows. Ex equal to integral minus infinity to plus infinity x of t into x star of t into dt equal to integral minus infinity to plus infinity x of t into dt into integral minus infinity to plus infinity x star of f into e power minus j 2 pi ft into df equal to integral minus infinity to plus infinity x star of f into df into integral minus infinity to plus infinity x of t into e power minus j 2 pi ft into dt equal to integral minus infinity to plus infinity modulus of x of f the whole square into df. Thus we conclude that Ex equal to integral minus infinity to plus infinity modulus of x of t the whole square equal to integral minus infinity to plus infinity modulus of x of f the whole square into df. This is Parseval's relation for aperiodic finite energy signals and expressed the principle of conservation of energy in the time and frequency domain. The spectrum x of f of a signal is in general complex values. Consequently, it is usually expressed in polar form as x of f equal to modulus of x of f into e power j theta of f, where modulus of x of f is the magnitude spectrum and theta of f is the phase spectrum. Theta of f equal to delta x of f. On the other hand, the quantity Sxx of f equal to modulus of x of f the whole square represents the distribution energy in the signal as a function of energy. Hence, Sxx of f is called the energy density spectrum of x of t. The integral Sxx of f over all frequencies gives the total energy in the signal. The energy in the signal x of t over a band of frequencies f1 less than or equal to f less than or equal to f1 plus delta f is integral limit f1 to f1 plus delta f Sxx of f into df. If the signal x of t is real, then modulus of x of minus f equal to modulus of x of f. Delta x of minus f equal to minus delta x of f. By combining Sx of f and modulus of x of minus f equations, we get Sxx of minus f equal to Sxx of f. The energy density spectrum of a real signal has even symmetry. Inverse systems and deconvolution. A linear time invariant system takes an input signal x of n and produces an output signal y of n, which is the convolution of x of n with the unit sample response h of n of the system. In many practical applications, we are given an output signal from a system whose characteristics are unknown, and we are asked to determine the input signal. For example, in the transmission of digital information at high data rates over telephone channels, it is well known that the channel distorts the signal and causes intersymbol interference among the data symbols. The interschool interference may cause errors when we attempt to recover the data. In such a case, the problem is to design a corrective system which, when cascaded with the channel, produces an output that in some sense corrects for the distortion caused by the channel and thus yields a replica of the desired transmitted signal. In digital communications, such a corrective system is called an equalizer. We call the corrective system an inverse system because the corrective system has a frequency response which is basically the reciprocal of the frequency response of the system that caused the distortion. Furthermore, since the distortive system yields an output y of n, that is, the convolution of the input x of n with the impulse response h of n, the inverse system operation that takes y of n and produces x of n is called deconvolution. If the characteristics of the distortive system are unknown, it is often necessary, when possible, to excite the system with a known signal, observe the output, compare it with the input, and in some manner determine the characteristics of the system. For example, in the digital communication problem just described, where the frequency response of the channel is unknown, the measurement of the channel frequency response can be accomplished by transmitting a set of equal amplitude sinusoids at different frequencies with a specified set of phases. Within the frequency band of the channel will attenuate and phase shift each of the sinusoids. By comparing the received signal with the transmitted signal, the receiver obtains a measurement of the channel frequency response which can be used to design the inverse system. The process of determining the characteristics of the unknown system, either h of n or h of omega, by a set of measurements performed on the system is called system identification. Invertibility of linear time invariant systems. A system is said to be invertible if there is a one-to-one correspondence between its input and output signals. This definition implies that if we know the output sequence y of n minus infinity less than n less than infinity of an invertible system T, we can uniquely determine its input x of n minus infinity less than n less than infinity. The inverse system with input y of n and output x of n is denoted by t power minus 1. Clearly, the cascade connection of a system and its inverse is equivalent to the identity system, since omega of n equal to t inverse into y of n equal to t inverse into t of x of n equal to x of n is called equation number 4.6.1. For example, the systems defined by the input-output relations y of n equal to a into x of n and y of n equal to x of n minus 5 are invertible, whereas the input-output relations y of n equal to x square of n and y of n equal to 0 represent non-invertible systems. As indicated above, inverse systems are important in many practical applications, including geophysics and digital communications. Let us begin by considering the problem of determining the inverse of a given system. We limit our discussion to the class of linear time invariant discrete time systems. Now suppose that the linear time invariant system T has an impulse response h of n, and let h1 of n denote the impulse response of the inverse system T inverse, then 4.6.1 is equivalent to the convolution equation. Omega of n equal to hl of n star h of n star x of n equal to x of n is called equation number 4.6.2. But 4.6.2 implies that h of n star hl of n equal to delta of n is called equation number 4.6.3. The convolution equation in 4.6.2 can be used to solve for h1 of n for given h of n. However, the solution of 4.6.3 in the time domain is usually difficult. A simpler approach is to transform 4.6.3 into the z domain and solve for t inverse. Thus, in the z transform domain, 4.6.3 becomes h of z into hl of z equal to 1. And therefore, the system function for the inverse system is hl of z equal to 1 divided by h of z. Is called equation number 4.6.4. If h of z has a rational system function, h of z equal to b of z divided by a of z is called equation number 4.6.5. Then hl of z equal to a of z divided by b of z is called 4.6.6. Thus, the zeros of h of z become the poles of the inverse system and vice versa. Furthermore, if h of z is an FIR system, then h1 of z is an all-pole system, or if h of z is an all-pole system, then h1 of z is an FIR system. Figure system T in cascade with its inverse T inverse. Minimum phase, maximum phase and mixed phase systems. The invertibility of a linear time invariant system is intimately related to the characteristics of the phase spectral function of the system. To illustrate this point, let us consider two FIR systems characterized by the system functions. H1 of z equal to 1 plus 1 by 2 into z inverse equal to z inverse into z plus 1 by 2 is called equation number 4.6.10. H2 of z equal to 1 by 2 plus z inverse equal to z inverse into 1 by 2 into z plus 1 is called equation number 4.6.11. The system in 4.6.10 has a 0 at z equal to minus 1 by 2 and an impulse response h of 0 equal to 1, h of 1 equal to 1 by 2. The system in 4.6.11 has a 0 at z equal to minus 2 and an impulse response h of 0 equal to 1 by 2, h of 1 equal to 1, which is the reverse of the system in 4.6.10. This is due to the reciprocal relationship between the zeros of h1 of z and h2 of z. In the frequency domain, the two systems are characterized by their frequency response functions, which can be expressed as modulus of h1 of omega equal to modulus of h2 of omega equal to square root of 5 by 4 plus cos omega is called equation number 4.6.12, and capital theta 1 of omega equal to minus omega plus tan inverse of sin omega divided by 1 by 2 plus cos omega is called equation number 4.6.13. Capital theta 2 of omega equal to minus omega plus tan inverse of sin omega divided by 2 plus cos omega. The magnitude characteristics for the two systems are identical because the zeros of h1 of z and h2 of z are reciprocals. Phase response characteristics for the system in 4.6.10 and 4.6.11, we observe that the phase characteristic capital theta 1 of omega for the first system begins at 0, phase at the frequency omega equal to pi, hence the net phase change capital theta 1 of pi minus capital theta 1 of 0 is 0. On the other hand, the phase characteristic for the system with the 0 outside, the unit circle undergoes a new phase change capital theta 2 of pi minus capital theta 2 of 0 equal to pi radians. As a consequence of these different phase characteristics, we call the first system a minimum phase system and the second system is called a maximum phase system. These definitions are easily extended to an FIR system of arbitrary length. To be specific, an FIR system of length m plus 1 has m zeros. Its frequency response can be expressed as h of omega equal to b naught into 1 minus z1 into e power minus j omega into 1 minus z2 into e power minus j omega, etc. 1 minus zm into e power minus j omega is called equation number 4.6.15, where zi denote the zeros and b naught is an arbitrary constant. When all the zeros are inside the unit circle, each term in the product of 4.6.15 corresponding to a real valued 0 will undergo a net phase change of 0 between omega equal to 0 and omega equal to pi. Also, each pair of complex conjugate factors in h of omega will undergo a net phase change of 0. Therefore, angle of h of pi minus angle of h of 0 equal to 0 is called equation number 4.6.16. And hence the system is called a minimum phase system. On the other hand, when all the zeros are outside the unit circle, a real valued 0 will contribute a net phase change of pi radians as the frequency varies from omega equal to 0 to omega equal to pi, and each pair of complex conjugate zeros will contribute a net phase change of 2 pi radians over the sample range of omega. Therefore, angle of h of pi minus angle of h of 0 equal to m pi is called equation number 4.6.17, which is the largest possible phase change for an FIR system with m zeros. Hence, the system is called maximum phase. It follows from the discussion Above that, angle of h maximum of pi greater than or equal to angle of h minimum of pi is called equation number 4.6.18. If the FIR system with M0 has some of its zeros inside the unit circle and the remaining zeros outside the unit circle, it is called a mixed phase system or a non-minimum phase system. Since the derivative of the phase characteristic of the system is a measure of the time delay that signal frequency components undergo in phasing through the system, a minimum phase characteristic implies that the delay characteristic is also maximum. Now suppose that we have an FIR system with real coefficients, then the magnitude square value of its frequency responses modulus of h of omega the whole square equal to h of z into h of z inverse at z equal to is called equation number 4.6.19. This relationship implies that if we replace the 0 zk of the system by its inverse 1 by zk, the magnitude characteristic of the system does not change. Thus, if we reflect a 0 zk that is inside the unit circle into a 0 1 by zk outside the unit circle, we see that the magnitude characteristic of the frequency response is invariant to such a change. If modulus of h of omega the whole square is the magnitude square frequency response of an FIR system having m zeros, there are 2 power m possible configurations for the m zeros, some of which are inside the unit circle and the remaining are outside the unit circle. Clearly, one configuration has all the zeros inside the unit circle, which corresponds to the minimum phase system. A second configuration has all the zeros outside the unit circle, which corresponds to the maximum phase system. The remaining 2 power m minus 2 configurations correspond to mixed phase systems. However, not all 2 power m minus 2 mixed phase configurations necessarily correspond to FIR system with real valued coefficients. Specifically, any pair of complex conjugate zeros yield 4 possible configurations. Decomposition of non-minimum phase pole zero systems. Any non-minimum phase pole zero system can be expressed as h of z equal to h minimum of z into h ap of z is called equation number 4.6.22. H minimum of z is a minimum phase system and h ap of z is an all-pass system. We demonstrate the validity of this assertion for the class of causal and stable systems with a rational system function. H of z equal to b of z divided by a of z. In general, if b of z has one or more roots outside the unit circle, we factor b of z into the product b1 of z into b2 of z, where b1 of z has all its roots inside the unit circle and b2 of z has all its roots outside the unit circle. Then b2 of z inverse has all its roots inside the unit circle. We define the maximum phase system h minimum of z equal to b1 of z into b2 of z inverse divided by a of z, and the all-pass system h ap of z equal to b2 of z divided by b2 of z inverse. Thus h of z equal to h minimum of z into h ap of z. Note that h ap of z is a stable all-pass maximum phase system. Group delay of non-minimum phase system. Based on the decomposition of a non-minimum phase system given by 4.6.22, we can express the group delay of h of z as tau g of omega equal to tau g minimum of omega plus rg ap of omega is called equation number 4.6.23. Since tau g ap of omega greater than or equal to 0 for 0 less than or equal to omega less than or equal to pi, it follows that tau g of omega greater than or equal to rg minimum of omega 0 less than or equal to omega less than or equal to pi. From 4.6.23, we conclude that among all pole zero systems having the same magnitude response, the minimum phase system has the smallest group delay. partial energy of non-minimum phase system. The partial energy of a causal system with impulse response h of n is defined as expectation of n equal to summation k equal to 0 to n modulus of h of k the whole square is called equation number 4.6.24. Among all the systems having the same magnitude response and the same total energy expectation of infinity, the minimum phase system has the largest partial energy. System identification and deconvolution. Suppose that we excite an unknown LTA system with an input sequence x of n and we observe the output sequence y of n. From the output sequence we wish to determine the impulse response of the unknown system. This is a problem in system identification which can be solved by deconvolution. Thus we have y of n equal to h of n star x of n equal to summation k equal to minus infinity to plus infinity h of k into x of n minus k is called equation number 4.6.25. An analytical solution of the deconvolution problem can be obtained by working with the Z transform of 4.6.25. In the Z transform domain, we have y of z equal to h of z into x of z, and hence h of z equal to y of z divided by x of z is called equation number 4.6.26. X of z and y of z are the Z transforms of the available input signal x of n and the observed output signal y of n respectively. This approach is appropriate only when there are closed form expressions for x of z and y of z. We observe that 4.6.26 determines system uniquely if it known that the system is causal. Alternatively, we can deal directly with the time domain expression given by 4.6.25. If the system is causal, we have y of n equal to summation k equal to 0 to n h of k into x of n minus k, where n greater than or equal to 0, and hence h of 0 equal to y of 0 divided by x of 0, h of n equal to y of n minus summation k equal to 0 to n minus 1 h of k into x of n minus k divided by x of 0, where n greater than or equal to 1 is called equation number 4.6.27. This recursive solution requires that x of 0 not equal to 0. However, we note again that when h of n has infinite duration, this approach may not be practical unless we truncate the recursive solution at same stage. Another method for identifying an unknown system is based on a cross correlation technique. Recall that the input-output cross correlation function given as Ryx of m equal to summation k equal to 0 to infinity h of k into Rxx of m minus k equal to h of n star Rxx of m is called equation number 4.6.28, where Ryx of m is the cross correlation sequence of the input x of n to the system with the output y of n of the system, and Ryx of m is the cross correlation sequence of the input signal. In the frequency domain, the corresponding relationship is Syx of omega equal to h of omega into Sxx of omega equal to h of omega into modulus of x of omega the whole square. Hence, h of omega equal to Syx of omega divided by Sxx of omega equal to Syx of omega divided by modulus of x of omega the whole square. These relations suggest that the impulse response h of n or the frequency response of an unknown system can be determined by cross correlation, the input sequence x of n with the output sequence y of n, and then solving the deconvolution problem by means of the recursive equation. The cross correlation method is an effective and practical method for system identification. Homomorphic deconvolution. The complex substrum is a useful tool for performing deconvolution in some applications such as seismic signal processing. Let us suppose that y of n is the output sequence of a linear time invariant system which is excited by the input sequence x of n. Then y of z equal to h of z into x of z, where h of z is the system function. The logarithm of y of z is cy of z equal to ln y of z equal to ln x of z plus ln h of z equal to cx of z plus ch of z is called equation number 4.6.31. Consequently, the complex substrum of the output sequence y of n is expressed as the sum of the substrum of x of n and h of n, that is cy of n equal to cx of n plus ch of n is called equation number 4.6.32. The convolution of the two sequences in the time domain corresponds to the summation of the substrum sequences in the substral domain. The system for performing these transformations is called a homomorphic system. Homomorphic system for obtaining the substrum cx of n of the sequence y of n. Separating the two substral components of low pass and high pass windows. In some applications such as seismic signal processing and speech signal processing, the characteristics of the substral sequences cx of n and ch of n are sufficiently different so that they can be separated in the substral domain. Specifically, suppose that ch of n has its main components in the vicinity of small values of n, whereas cx of n has its components concentrated at large values of n. ch of n is low pass and cx of n is high pass. We can then separate ch of n using appropriate low pass and high pass windows. Thus, dou h of n equal to dou y of n into omega 1 p of n is called equation number 4.6.33, and dou x of n equal to dou y of n into omega h p of n is called equation number 4.6.34, where omega 1 p of n equal to 1 for modulus of n less than or equal to n1, then 0 otherwise, is called equation number 4.6.35. Omega hp of n equal to 0 for modulus of n less than or equal to n1, 1 for modulus of n greater than n1. Once we state the substrum sequences ch of n and cx of n by windowing the sequences x of n and h of n are obtained by passing ch of n and cx of n through the inverse homomorphic system. Inverse homomorphic system for recovering the sequences x of n and h of n from the corresponding substra. Linear time invariant systems as frequency selective filters. The term filter is commonly used to describe a device that discriminates according to some attribute of the objects applied at its input, what passes through it. For example, an air filter allows air to pass through it but prevents dust particles that are present in the air from passing through. A linear time invariant system also performs a type of discrimination or filtering among the various frequency components at its input. The nature of this filtering action is determined by the frequency response characteristics h of omega, which in turn depends on the choice of the system parameters. Example, the coefficients ak and bk in the difference equation characterization of the system. By proper selection of the coefficients, we can design frequency selective filters that pass signals with frequency components in some bands while they attenuate signals containing frequency components in other frequency bands. In general, a linear time invariant system modifies the input signal spectrum x of omega according to its frequency response h of omega to yield an output signal with spectrum y of omega equal to h of omega into x of omega. H of omega acts as a weighting function or a spectral shaping function to the different frequency components in the input signal. Any linear time invariant system can be considered to be a frequency shaping filter, even though it may not necessarily completely block or all frequency components. The terms linear time invariant system and filter are synonymous and are often used interchangeably. We use the term filter to describe a linear time invariant system used to perform spectral shaping or frequency selective filtering. Filtering is used in digital signal processing in a variety of ways. For example, removal of undesirable noise from desired signals. Spectral shaping such as equalization of communication channels, signal detection in radar, sonar, and communications, and for performing spectral analysis of signals and so on. Ideal filter characteristic. Filters are usually classified according to their frequency domain characteristic as low pass, high pass, band pass, and band stop or band elimination filters. These ideal filters have a constant gain, usually taken as unity gain, pass band characteristic, and a zero gain in their stop band. Another characteristic of an ideal filter is a linear phase response. To demonstrate this point, let us assume that a signal sequence x of n with the frequency components confined to the frequency range omega 1 less than omega 2 is passed through a filter with the frequency response. H of omega equal to c into e power minus j omega n naught, where omega 1 less than omega 2, then 0 otherwise, where c and n naught are constants. The signal at the output of the filter has a spectrum. Gamma of omega equal to x of omega into h of omega equal to c into x of omega into e power minus j omega n naught, where omega 1 less than omega. In conclusion, ideal filters have a constant magnitude characteristics and a linear phase characteristics within their pass band. In all cases, such filters are not physically realizable but serve as a mathematical idealization of practical filters. For example, the ideal low-pass filter has an impulse response hjp of n equal to sin omega naught pi n divided by pi n, where minus infinity less than n less than infinity. This filter is not causal and it is not absolutely summable, and therefore it is also unstable. This ideal filter is physically unrealizable. The basic principle underlying the pole zero placement method is to locate poles near points of the unit circle corresponding to frequencies to be emphasized and to place zeros near the frequencies to be de-emphasized. Furthermore, the following constraints must be imposed. All poles should be placed inside the unit circle in order for the filter to be stable. However, zeros can be placed anywhere in the z-plane. All complex zeros and poles must occur in complex conjugate pairs in order for the filter coefficients to be real. From our previous discussion, we recall that for a given pole zero pattern, the system function h of z can be expressed as h of z equal to summation k equal to 0 to m bk into z power minus k divided by 1 plus summation k equal to 1 to n ak into z power minus k equal to b naught into pi k equal to 1 to m 1 minus zk into z power minus 1 divided by pi k equal to 1 to n 1 minus pk into z power minus 1, where b naught is a gain constant selected to be normalized the frequency response at some specified frequency, that is b naught is selected such that modulus of h of omega naught equal to 1, where omega naught is a frequency in the pass band of the filter. Usually n is selected to equal or exceed m, so that the filter has more non-trivial poles than zeros. We can see in the figure low pass, high pass, band pass, all pass. Figure magnitude responses for some ideal frequency selective discrete time filters. Low pass, high pass and band pass filters. In the design of low pass digital filters, the poles should be placed near the unit circle at points corresponding to low frequencies near omega equal to 0, and 0 should be placed near or on the unit circle at points corresponding to high frequencies near omega equal to n. The opposite holds true for high pass filters. The gain G was selected as 1A so that the filter has unity gain at omega equal to 0. The gain of this filter at high frequencies is relatively small. The addition of a 0 at z equal to minus 1 further attenuates the response of the filter at high frequencies. This leads to a filter with a system function h2 of z equal to 1 minus a divided by 2 into 1 plus z inverse divided by 1 minus a into z inverse. And high frequency response characteristics that is also illustrated in figure 4.45. In this case, the magnitude of h2 of omega goes to 0 at omega equal to n. Similarly, we can obtain simple high-pass filters by folding the pole 0 locations of the low-pass filters about the imaginary axis in the z-plane. Thus, we obtain the system function h3 of z equal to 1 minus a divided by 2 into 1 minus z inverse divided by 1 plus a into z inverse. Low pass, high pass. Pole 0 pattern for several low pass and high pass filters. Magnitude and phase response of 1. A single pole filter and 2. A one pole 1-0 filter. A simple low pass to high pass filter transformation. Suppose that we have designed a prototype low pass filter with the impulse response h1p of n. By using the frequency translation property of the Fourier transform, it is possible to convert the prototype filter to either a band pass or a high pass filter. In this section, we present a simple frequency transformation for converting a low pass filter into a high pass filter and vice versa. If h1p of n denote the impulse response of a low pass filter with frequency response h1p of omega, a high pass filter can be obtained by translating h1p of omega by n radians, that is replacing omega by omega minus n. Thus, hp of omega equal to h1p of omega minus pi, where hp of omega is the frequency response of the high pass filter. Since a frequency translation of n radians is equivalent to multiplication of the impulse response h1p of n by e power jnn. The impulse response of the high pass filter is hp of n equal to e power j pi whole power n, h1p of n equal to minus 1 whole power n into h1p of n. Therefore, the impulse response of the high pass filter is simply obtained from the impulse response of the low pass filter by changing the signs of the odd numbered samples in h1p of n. Conversely, h1p of n equal to minus 1 whole power n into hhp of n. If the low pass filter is described by the difference equations, y of n equal to minus summation k equal to 1 to n ak into y of n minus k plus summation k equal to 0 to m bk into x of n minus k. Its frequency response is h1p of omega equal to summation k equal to 0 to m bk into e power minus j omega k divided by 1 plus summation k equal to 1 to n ak into e power minus j omega k. Now, if we replace omega with omega minus n in 4.5.16, then hp of omega equal to summation k equal to 0 to m minus 1 whole power k into bk e power minus j omega k divided by 1 plus summation k equal to 1 to n minus 1 whole power k into ak into e power minus j omega k, which corresponds to the difference equation y of n equal to minus summation k equal to 1 to n minus 1 whole power k ak into y of n minus k plus summation k equal to 0 to m minus 1 whole power k into bk into x of n minus k. Digital resonators. A digital resonator is a special two-pole bandpass filter with the pair of complex conjugate poles located near the unit circle. The name resonator refers to the fact that the filter has a large magnitude response, that is, it resonates in the vicinity of the pole location. The angular position of the pole determines the resonant frequency of the filter. Digital resonators are useful in many applications, including simple bandpass filtering and speech generation. In the design of a digital resonator with the resonant peak at or near omega equal to omega naught, we select the complex conjugate poles at P1.2 equal to R into e power plus or minus j omega naught, where 0 less than or less than 1. In addition, we select up to 2 zeros. One choice is to locate the zeros at the origin. The other choice is to locate a 0 at z equal to 1 and a 0 at z equal to minus 1. The second choice completely eliminates the response of the filter at frequencies omega equal to 0 and omega equal to n, and it is useful in many practical applications. The system function of the digital resonator with zeros at the origin is h of z equal to b naught divided by 1 minus r into e power j omega naught into z power minus 1 into 1 minus r into e power minus j omega naught into z power minus 1. Then h of z equal to b naught divided by 1 minus 2r cos omega naught into z power minus 1 plus r square into z power minus 2. Since modulus of h of omega has its peak at or near omega equal to omega naught, we select the aim b naught so that modulus of h of omega naught equal to 1. We obtain h of omega naught equal to b naught divided by 1 minus r into e power j omega naught into e power minus j omega naught into 1 minus r into e power minus j omega naught into e power minus j omega naught equal to b naught divided by 1 minus r into 1 minus r into e power minus j 2 omega naught, and hence modulus of h of omega naught equal to b naught divided by 1 minus r into square root of 1 plus r square minus 2r cos 2 omega naught equal to 1. Thus the desired normalization factor is b naught equal to 1 minus r into square root of 1 plus r square minus 2r cos 2 omega naught. The frequency response of the resonator in 4.5.19 can be expressed as modulus of h of omega equal to b naught divided by u1 of omega into u2 of omega. Capital theta of omega equal to 2 omega minus pi 1 of omega minus pi 2 of omega, where u1 of omega and u2 of omega are the magnitudes of the vectors from p1 and p2 to the point omega in the unit circle, or the corresponding angles of these two vectors. The magnitudes u1 of omega and u2 of omega may be expressed as u1 of omega equal to square root of 1 plus r square minus 2r cos omega naught minus omega, u2 of omega equal to square root of 1 plus r square minus 2r cos omega naught plus omega. For any value of r, u1 of omega takes its minimum value 1 minus r at omega equal to omega naught. The product u1 of omega, u2 of omega reaches a minimum value at the frequency omega r equal to cos inverse of 1 plus r square divided by 2r into cos omega naught, which defines precisely the resonant frequency of the filter, where r is very close to unity, omega r approximately equal to omega naught, which is the angular position of the pole. As r approaches unity, the resonance peak becomes sharper because measure of the sharpness of the resonance is provided by the 3 dp bandwidth delta omega of the filter. For values of r close to unity, delta omega approximately equal to 2 times of 1 minus r. Phase response undergoes its greatest rate of change near the resonant frequency. If the zeros of the digital resonator are placed at z equal to 1 and z equal to minus 1, the resonator has the system function h of z equal to g into 1 minus z power minus 1 into 1 plus z power minus 1 divided by 1 minus r into e power j omega naught into z power minus 1 into 1 minus r into e power minus j omega naught into z power minus 1. And a frequency response characteristic h of omega equal to b naught into 1 minus e power minus j 2 omega divided by 1 minus r into e power j omega naught minus omega into 1 minus r into e power minus j omega naught plus omega. The zeros at z equal to plus or minus 1 affect both the magnitude and phase response of the resonator. For example, the magnitude response is modulus of h of omega equal to b naught into n of omega divided by u1 of omega into u2 of omega, where n of omega is defined as n of omega equal to square root of 2 into 1 minus cos 2 omega. Due to the presence of the zero factor, the resonant frequency is altered. The bandwidth of the filter is also altered. Notch filters. A notch filter is a filter that contains one or more deep notches, or ideally perfect nulls in its frequency response characteristic. Notch filters are useful in many applications where specific frequency components must be eliminated. For example, instrumentation and recording systems require that the power line frequency of 60 Hz and its harmonics be eliminated. To create a null in the frequency response of a filter at a frequency omega naught, we simply introduce a pair of complex conjugate zeros on the unit circle at an angle omega naught, that is Z1.2 equal to e power plus or minus j omega naught. Thus, the system function for an FIR notch filter is simply h of z equal to b naught into 1 minus e power j omega naught into z power minus 1 into 1 minus e power minus j omega naught into z power minus 1 equal to b naught into 1 minus 2 cos omega naught into z power minus 1 plus z power minus 2 is called equation number 4.5.30. The problem with the FIR notch filter is that the notch has a relatively large bandwidth, which means that other frequency components around the desired null are severely attenuated. To reduce the bandwidth of the null, we can resort to a more sophisticated longer FIR filter. Alternatively, we could, in an ad hoc manner, attempt to improve on the frequency response characteristics by introducing poles in the system function. Frequency response characteristics of a notch filter. Suppose that we place a pair of complex conjugate poles at P1.2 equal to or into e power plus or minus j omega naught. The effect of the poles is to introduce a resonance in the vicinity of the null and thus to reduce the bandwidth of the notch. The system function for resulting filter is h of z equal to b naught into 1 minus 2 into cos omega naught into z power minus 1 plus z power minus 2 divided by 1 minus 2 or cos omega naught into z power minus 1 plus r square into z power minus 2. In addition to reducing the bandwidth of the notch, the introduction of a pole in the vicinity of the null may result in a small ripple in the pass band of the filter due to the resonance created by the pole. The effect of the ripple can be reduced by introducing additional poles and or zeros in the system function of the not notch filter. The major problem with this approach is that it is basically an ad hoc trial and error method. COM filters. A COM filter can be viewed as a notch filter in which the nulls occur periodically across the frequency band. Hence, the analogy to an ordinary comb that has periodically spaced teeth. COM filters find applications in a wide range of practical systems, such as in the rejection of power line harmonics, in the separation of solar and lunar components from ionospheric measurements of electron concentration, and in the suppression clutter from fixed objects in moving target indicator MTI radars. To illustrate a simple form of a COM filter, consider a moving average FIR filter described by the difference equation. Y of n equal to 1 divided by m plus 1 into summation k equal to 0 to m x into n minus k. The system function of this filter is h of z equal to 1 divided by m plus 1 into summation k equal to 0 to m z power minus k equal to 1 divided by m plus 1 into 1 minus z power minus of m plus 1 divided by 1 minus z power minus 1, and its frequency response is h of omega equal to e power minus omega into m by 2 divided by m plus 1 into sin omega m plus 1 by 2 divided by sin omega by 2. Figure magnitude response characteristics for the comb filter given by 4.5.32 with m equal to 10. From above figure, we observe that the filter has zeros on the unit circle at z equal to e power j 2 pi k divided by m minus 1, where k equal to 1, 2, 3, etc. m is called equation number 4.5.35. Note that the pole at z equal to 1 is actually cancelled by the 0 at z equal to 1, so that in effect the FIR filter does not contain poles outside z equal to 0. A plot of the magnitude characteristics of 4.5.34 clearly illustrates the existence of the periodically spaced zeros in frequency at omega k equal to 2 pi k divided by m plus 1 for k equal to 1, 2, etc. m. In more general terms, we can create a comb filter by taking an FIR filter with system function h of z equal to summation k equal to 0 to m h of k into z power minus k is called equation number 4.5.36, and replacing z by z power l, where l is a positive integer. Thus, the new FIR filter has a system function hl of z equal to summation k equal to 0 to m h of k into z power minus kl is called equation number 4.5.37. If the frequency response of the original FIR filter is h of omega, the frequency response of the FIR in 4.5.37 is hl of omega equal to summation k equal to 0 to m h of k into e power minus j k l omega is called equation number 4.5.38. Consequently, the frequency response characteristics hl of omega is simply an L order repetition of h of omega in the range 0 less than or equal to omega less than or equal to 2 pi. Now, suppose that the original FIR filter with the system function h of z as a spectral null, that is a 0, at some frequency omega naught, then the filter with system function hl of z as periodically spaced nulls at omega k equal to omega naught plus 2 pi k divided by l, k equal to 0, 1, 2, etc. l minus 1. This FIR filter can be viewed as an FIR filter of length 10, but only 4 of the 10 filter coefficients are non-zero. Let us now return to the moving average filter with the system function given by 4.5.33. Suppose that we replace z by z power l, then the resulting comb filter as the system function hl of z equal to 1 divided by m plus 1 into 1 minus z power minus l of m plus 1 divided by 1 minus z power minus l is called equation number 4.5.39, and the frequency response hl of omega equal to 1 divided by m plus 1 into sin omega l of m plus 1 by 2 divided by sin omega l by 2 into e power minus j omega l m by 2 is called equation number 4.5.40. This filter has zeros on the unit circle at e power j 2 pi k divided by l of m plus 1 is called equation number 4.5.41. For all integer values of k except k equal to 0, l, 2l, etc. ml. Figure comb filter with the frequency response hl of omega obtained from h of omega. Realization of an FIR comb filter having m equal to 3 and L equal to 3. All-pass filter. An all-pass filter is defined as a system that has a constant magnitude response for all frequencies, that is, modulus of h of omega equal to 1 for 0 less than or equal to omega less than or equal to pi is called equation number 4.5.42. The simplest example of an all-pass filter is a pure delay system with system function h of z equal to z power minus k. The system passes all signals without modification except for a delay of k samples. This is a trivial all-pass system that has a linear phase response characteristic. A more interesting all-pass filter is described by the system function h of z equal to an plus an minus 1 into z power minus 1 plus etc. plus a1 into z power minus n plus 1 plus z power minus n divided by 1 plus a1 into z power minus 1 plus etc. plus an into z power minus n equal to summation k equal to 0 to n ak into z power minus n plus k divided by summation k equal to 0 to n ak into z power minus k where a not equal to 1 is called equation number 4.5.43. Where all the filters coefficients ak are real, if we define the polynomial a of z as a of z equal to summation k equal to 0 to n ak into z power minus k where a not equal to 1, then 4.5.43 can be expressed as h of z equal to z power minus n into a of z power minus 1 divided by a of z is called equation number 4.5.44. Since modulus of h of omega the whole square equal to h of z into h of z power minus 1 at z equal to e power j omega equal to 1, the system given by 4.5.44 is an all-pass system. Furthermore, if z0 is a pole of h of z, then 1 divided by z0 is a 0 of h of z, that is, the poles and zeros are reciprocals of one another. The most general form for the system function of an all-pass system with real coefficients expressed in factored form in terms of poles and zeros is h ap of z equal to pi k equal to 1 to n r z power minus 1 minus alpha k divided by 1 minus alpha k into z power minus 1 into pi k equal to 1 to n r minus 1 minus beta k into z power minus 1 minus beta k star divided by 1 minus beta k into z power minus 1 into 1 minus beta k star into z power minus 1 is called equation number 4.5.45, where there are n r real poles and zeros and n c complex conjugate pairs of poles and zeros. For causal and stable systems, we require that minus 1 less than alpha k less than 1 and modulus of beta k less than 1. For a single pole, single zero, all-pass system we have h ap of omega equal to e power L omega minus r into e power minus j theta divided by L minus r into e power j theta into e power minus j omega. Hence, capital theta ap of omega equal to minus omega minus 2 tan inverse r into sine of omega minus theta divided by 1 minus r into cos of omega minus theta, and tau p of omega equal to minus d capital theta ap of omega divided by d omega equal to 1 minus r square divided by 1 plus r square minus 2r into cos omega minus theta is called equation number 4.5.46. We note that for a causal and stable system r less than 1 and hence tq of omega greater than or equal to 0. Since the group delay of a higher order pole zero system consists of a sum of positive terms, the group delay will always be positive. All pass filters find application as phase equalizers when placed in cascade with a system that has an undesired phase response, and a phase equalizer is designed to compensate for the poor phase characteristics of the system and therefore to produce an overall linear phase response. Digital sinusoidal oscillators. A digital sinusoidal oscillator can be viewed as a limiting form of a two-pole resonator for which the complex conjugate poles lie on the unit circle. For our previous discussion of second-order systems, we recall that a system with the system function h of z equal to b0 divided by 1 plus a1 into z power minus 1 plus a2 into z power minus 2 is called equation number 4.5.47. And parameters a1 equal to minus 2r cos omega naught and a2 equal to r square is called equation number 4.5.48. As complex conjugate poles at p equal to r into e power plus or minus j omega naught and a unit sample response h of n equal to b naught into r power n divided by sin omega naught sin of n plus 1 into omega naught u of n is called equation number 4.5.49. If the poles are placed on the unit circle or equal to 1 and b naught is set to a sin omega naught, then h of n equal to a sin of n plus 1 omega naught u of n is called equation number 4.5.50. Thus the impulse response of the second order system with complex conjugate poles on the unit circle is sinusoid, and the system is called a digital sinusoid oscillator or a digital sinusoidal generator. A digital sinusoidal generator is a basic component of a digital frequency synthesizer. Digital sinusoidal generator. The corresponding difference equation for above system is y of n equal to minus a1 into y of n minus 1 minus y of n minus 2 plus b naught into delta of n is called equation number 4.5.51, where the parameters a1 equal to minus 2 cos omega naught and b naught equal to a sin omega naught, and the initial conditions are y of minus 1 equal to y of minus 2 equal to 0. By iterating the difference equation in 4.5.51, we obtain y of 0 equal to a sin omega naught, y of 1 equal to 2 cos omega naught into y of 0 equal to 2a sin omega naught cos omega naught equal to a sin 2 omega naught, y of 2 equal to 2 cos omega naught y of 1 minus y of 0 equal to 2a cos omega naught sin 2 omega naught minus a sin omega naught equal to a into within the bracket 4 cos square omega naught minus 1 into sin omega naught equal to 3a sin omega naught minus 4 sin cube omega naught equal to a sin 3 omega naught. We note that the application of the impulse at n equal to 0 serves the purpose of beginning the sinusoidal oscillation. Thereafter the oscillation is self-sustaining because the system has no damping, that is r equal to 1. The sinusoidal oscillation obtained from the system in 4.5.51 can also be obtained by setting the input to 0 and setting the initial conditions to y of minus 1 equal to 0, y of minus 2 equal to minus a sin omega naught. Thus the zero input response to the second order system described by the homogeneous difference equation. Y of n equal to minus a1 into y of n minus 1 minus y of n minus 2 is called equation number 4.5.52. With the initial conditions y of minus 1 equal to 0 and y of minus 2 equal to minus a sin omega naught is exactly the same as the response of 4.5.51 to an impulse excitation. In fact, the difference equation in 4.5.52 can be obtained directly from the trigonometric identity. Sin alpha plus sin beta equal to 2 sin alpha plus beta by 2 into cos alpha minus beta by 2 is called equation number 5.53. Per definition, alpha equal to n plus 1 into omega naught, beta equal to n minus 1 into omega naught, and y of n equal to sine of n plus 1 into omega naught. In some practical applications involving modulation of two sinusoidal carrier signals in phase quadrature, there is a need to generate the sinusoids a sin omega naught n and a cos omega naught n. These signals can be generated from the so-called coupled form oscillator, which can be obtained from the trigonometric formulas. Cos of alpha plus beta equal to cos alpha cos beta minus sin alpha sin beta. Sin of alpha plus beta equal to sin alpha cos beta plus cos alpha sin beta. Or by definition, alpha equal to n omega naught, beta equal to omega naught, and yc of n equal to cos n omega naught u of n is called equation number 4.5.54. Ys of n equal to sin n omega naught into u of n is called equation number 4.5.55. Thus we obtain the two coupled difference equations. Yc of n equal to cos omega naught into yc of n minus 1 minus sin omega naught into yn of n minus 1 is called equation number 4.5.56. Yn of n equal to sin omega naught into yc of n minus 1 plus cos omega naught into ys of n minus 1 is called equation number 4.5.57, which can also be expressed in matrix form as yc of n, ys of n equal to cos omega naught minus sin omega naught, then the second row sin omega naught cos omega naught, then yc of n minus 1, ys of n minus 1 is called equation number 4.5.58. This is a two output system which is not driven by any input but which requires the initial conditions yc of minus 1 equal to a cos omega naught and ys of minus 1 equal to minus a sin omega naught in order to begin its self-sustaining oscillations. Realization of the coupled form oscillator. Properties of the Fourier transform for discrete time signals. Fourier transform for aperiodic finite energy discrete time signals possess a number of properties that are useful in reducing the complexity of frequency analysis problems. Similar properties hold for the Fourier transform of aperiodic finite energy continuous time signals. For convenience, we adopt the notation x of omega equal to f of x of n equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n is called equation number 4.3.1. For direct transform and x of n is equivalent to f inverse of x of omega equal to 1 by 2 pi integral under 2 pi x of omega into e power j omega n d omega is called equation number 4.3.2. For the inverse transform, we also refer x of n and x of omega as a Fourier transform pair and denote this relationship with the notation x of n is related to x of omega in the presence of f is called equation number 4.3.3. The range of integration is always 2 pi, independent of the specific characteristics of the signal within the fundamental interval. Symmetry properties of the Fourier transform. Suppose that both the signal x of n and its transform x of omega are complex valued functions, then they can be expressed in rectangular form as x of n equal to x r of n plus j into x I of n is called equation number 4.3.4. X of omega equal to x r of omega plus j into x1 of omega is called equation number 4.3.5. By substituting 4.3.4 and e power minus j omega equal to cos omega minus j into sin omega into 4.3.1 equation and separating real and imaginary parts, we obtain xr of omega equal to summation n equal to minus infinity to plus infinity xr of n into cos omega n plus xl of n into sin omega n is called equation number 4.3.6. xl of omega equal to minus summation n equal to minus infinity to plus infinity xr of n into sin omega n minus xj of n into cos omega n. In similar manner, by substituting 4.3.5 and e power j omega equal to cos omega plus j sin omega into 4.3.2 we obtain is called equation number 4.3.7. xr of n equal to 1 by 2 pi integral under 2 pi xr of omega into cos omega n minus xl of omega into sin omega n into d omega is called equation number 4.3.8. xl of n equal to 1 by 2 pi integral under 2 pi xr of omega into sin omega n plus xl of omega into cos omega n into d omega is called equation number 4.3.9.
Real signals. If x of n is real, then xr of n equal to x of n, xt of n equal to 0. Hence, equation number 4.3.6 and 4.3.7 reduce to xr of omega equal to summation n equal to minus infinity to plus infinity x of n into cos omega n, called equation number 4.3.10, and xr of omega equal to minus summation n equal to minus infinity to plus infinity x of n into sin omega n is called equation number 4.3.11. Since cos of minus omega n equal to cos omega n and sin of minus omega n equal to minus sin omega n, it follows from equation number 4.3.10 and 4.3.11 that xr of minus omega equal to xr of omega is called even, and also equation number 4.3.12 xl of minus omega equal to minus xl of omega is odd, and also equation number 4.3.13. If we combine equations 4.3.12 and 4.3.13 into a single equation, we have x star of omega equal to x of minus omega. In this case, we say that the spectrum of a real signal has Hermitian symmetry. Magnitude and phase spectra for real signals are modulus of x of omega equal to square root of x square r of omega plus x square L of omega is called equation number 4.3.15. Angular point x of omega equal to tan inverse of xl of omega divided by xr of omega is called equation number 4.3.16. As a sequence of 4.3.12 and 4.3.13, the magnitude and phase spectra also possess a symmetry properties. Modulus of x of omega equal to modulus of x of minus omega called even, and also equation 4.3.17. Angular point x of minus omega equal to minus angular point x of omega called odd, and also equation number 4.3.18. In case of the inverse transform of a real values signal, x of n equal to 1 divided by 2 pi integral under the limit 2 pi x r of omega cos omega n minus xl of omega sin omega n d omega is called equation number 4.3.19. Since both products x r of omega cos omega n and xl of omega sin omega n are even functions of omega, we have x of n equal to 1 by pi integral 0 to pi x r of omega cos omega n minus x L of omega sin omega n into d omega is called equation number 4.3.20. Real and even signals. If x of n is real and even, that is x of minus n equal to x of n, then x of n into cos omega n is even and x of n into sin omega n is odd. Xk of omega equal to x of 0 plus 2 times of summation n equal to 1 to infinity x of n into cos omega n is even, xl of omega equal to 0, then x of n equal to 1 by pi integral 0 to pi x r of omega cos omega n into d omega. Thus real and even signals possess real value spectra which in addition are even functions of the frequency variable omega. Real and odd signals. If x of n is real and odd, that is x of minus n equal to minus x of n, then x of n into cos omega n is odd and x of n into sin omega n is even. X r of omega equal to 0, x t of omega equal to minus 2 into summation n equal to 1 to infinity x of n into sin omega n is odd. X of n equal to minus 1 by pi integral 0 to pi x L of omega into sin omega n into d omega. Thus real valued odd signals possess purely imaginary valued spectral characteristics which in addition are odd function of the frequency variable omega. Purely imaginary signals. In this case, x r of n equal to 0 and x of n equal to j into x1 of n. Thus, x r of omega equal to summation n equal to minus infinity to plus infinity x L of n into sin omega n is odd. X L of omega equal to summation n equal to minus infinity to plus infinity x L of n into cos omega n is even. X L of n equal to 1 by pi integral 0 to pi x r of omega into sin omega n plus x L of omega into cos omega n into d omega. If x L of n is odd, then x r of omega equal to 2 times of summation n equal to 1 to infinity x L of n into sin omega n is odd. X L of omega equal to 0, x L of n equal to 1 by pi integral 0 to pi x r of omega into sin omega n into d omega. Similarly, x L of n is even, then x r of omega equal to 0, x L of omega equal to x L of 0 plus 2 times of summation n equal to 1 to infinity x L of n into cos omega n is even. Then x L of n equal to 1 by pi integral 0 to pi x L of omega into cos omega n into d omega. An arbitrary, possibly complex valued signal x of n can be decomposed as x of n equal to x r of n plus j into x L of n equal to even x r of n plus odd x r of n plus j into even x L of n plus odd xl of n equal to even x of n plus odd x of n, where by definition even x of n equal to even xr of n plus j into even xl of n equal to 1 by 2 x of n plus x star of minus n. Odd x of n equal to odd xr of n plus j into odd xl of n equal to 1 by 2 into x of n minus x star of minus n. The subscripts e and 0 denote even and odd signal component respectively. From x of n value from above equation and Fourier transform properties, we get x of n equal to modulus of even xr of n plus j into even xl of n plus modulus of odd xr of n plus j into odd xl of n. X of omega equal to modulus of even xr of omega plus j into even xl of omega plus modulus of odd xk of omega plus j into odd xl of omega. Figure summary of symmetry properties for the Fourier transform. Table symmetry properties of the discrete time Fourier transform. We can see in the table the sequences and DTFT, that is called discrete time Fourier transform. Fourier transform theorems and properties. Linearity. If x1 of n is related to x1 of omega and x2 of n is related to x2 of omega, then a1 into x1 of n plus a2 into x2 of n is related to a1 into x1 of omega plus a2 into x2 of omega. The Fourier transform of a linear combination of two or more signal is equal to the same linear combination of the Fourier transforms of the individual signals. Time shifting. If x of n is related to x of omega, then x of n minus k is related to e power minus j omega k into x of omega. The proof of this property follows immediately from the Fourier transform of x of n minus k, making a change in the summation index. F of x of n minus k equal to x of omega e power minus j omega k equal to modulus of x of omega e power j into modulus of angular point x of omega minus omega k. If an angle is shifted in the time domain by k samples, its magnitude spectrum remains unchanged. The phase spectrum is changed by an amount minus omega k. Shifting by k in the time domain is equivalent to multiplying the spectrum by e power minus j omega k in the frequency domain. Time reversal. If x of n is related to x of omega, then x of minus n is related to x of minus omega. This property can be established by performing Fourier transformation of x of minus n and making a simple change in the summation index. Thus, Fourier transform of x of minus n equal to summation L equal to minus infinity to plus infinity x of L into e power j omega k equal to x of minus omega. If x of n is real, then Fourier transform of x of minus n equal to x of minus omega equal to modulus of x of minus omega e power j angular point of x of minus omega equal to modulus of x of omega e power minus j angular point x of omega. If a signal is folded about the origin in time, its magnitude spectrum remains unchanged and the phase spectrum undergoes a change in sign, phase reversal. Convolution theorem. If x1 of n is related to x1 of omega and x2 of n is related to x2 of omega, then x of n equal to x1 of n star x2 of n is related to x of omega equal to x1 of omega into x2 of omega. To prove above equation, we recall the convolution formula. X of n equal to x1 of n star x2 of n equal to summation k equal to minus infinity to plus infinity x1 of k into x2 of n minus k. By multiplying both sides of this equation by the exponential expectation of minus j omega n and summing overall n, we obtain x of n equal to summation n equal to minus infinity to plus infinity x of n e power minus j omega n equal to summation n equal to minus infinity to plus infinity into summation k equal to minus infinity to plus infinity x1 of k into x2 of n minus k into e power minus j omega n. After interchanging the order of the summations and making simple change in the summation index, the right hand side of this equation reduces to the product x1 of omega into x2 of omega. If we convolve two signals in a time domain, then this is equivalent to multiplying their spectra in the frequency domain. The correlation theorem. If x1 of n is related to x1 of omega and x2 of n is related to x2 of omega, then or x1 x2 of m is related to s x1 x2 of omega is equal to x1 of omega into x2 of minus omega. The proof of above equation is similar to the convolution theorem. In this case, we have or x1 x2 of n is equal to summation k equal to minus infinity to plus infinity x1 of k into x2 of k minus n. By multiplying both sides of this equation by the exponential expectation of minus j omega n and summing overall n, we obtain s x1 x2 of omega equal to summation n equal to minus infinity to plus infinity or x1 x2 of n into e power minus j omega n equal to summation n equal to minus infinity to plus infinity into summation k equal to minus infinity to plus infinity x1 of k into x2 of k minus n into e power minus j omega n. Finally, we interchange the order of the summations and make a change in the summation index. Thus, the
right hand side of the equation reduces to x1 of omega into x2 of minus omega. The function Sx1 x2 of omega is called the cross energy density spectrum of the signals x1 of n and x2 of n. The Wiener-Khinchin theorem. Let x of n be a real signal, then Rxx of L is related to Sxx of omega. The energy spectral density of an energy signal is the Fourier transform of its autocorrelation sequence. The autocorrelation sequence of a signal and its energy spectral density contain the same information about the signal. Since neither of these contains any phase information, it is impossible to uniquely reconstruct the signal from the autocorrelation function or the energy density spectrum. Frequency shifting. If x of n is related to x of omega, then e power j omega naught n x of n is related to x of omega minus omega naught. This property is easily proved by direct substitution into the analysis equation. Multiplication of a sequence x of n by e power j omega naught n is equivalent to a frequency translation of the spectrum x of omega by omega naught. Figure. Illustration of the frequency shifting property of the Fourier transform. The modulation theorem. If x of n is related to x of omega, then x of n into cos omega naught n is related to 1 by 2 into x of omega plus omega naught plus x of omega minus omega naught. To prove the modulation theorem, we first express the signal cos omega naught n equal to 1 by 2 into e power j omega n plus e power minus j omega n. Upon multiplying x of n by these two exponentials and using the frequency shifting property described in the preceding section, we obtain the desired result. Figure. Graphical representation of modular theorem. Percival's theorem. If x1 of n is related to x2 of omega and x2 of n is related to x2 of omega, then summation n equal to minus infinity to plus infinity x1 of n into x2 star of n equal to 1 by 2 pi integral minus pi to pi x1 of omega into x2 star of omega into d omega. To prove this theorem, we use x of omega equal to f of x of n equal summation n equal to minus infinity to plus infinity x of n e power minus j omega n. To eliminate x1 of omega, 1 by 2 pi integral 2 pi summation n equal to minus infinity to plus infinity x1 of n into e power minus j omega n into x2 star of omega into d omega equal to summation n equal to minus infinity to plus infinity x1 of n into 1 by 2 pi integral 2 pi x2 star of omega e power minus j omega n d omega equal to summation n equal to minus infinity to plus infinity
x1 of n into x2 star of n. In the special case where x2 of n equal to x1 of n equal to x of n, Parseval's relation reduces to summation n equal to minus infinity to plus infinity modulus of x of n the whole square equal to 1 by 2 pi integral 2 pi modulus of x of omega the whole square into d omega. The left hand side of the above equation is the energy Ex of the signal x of n. It is also equal to the autocorrelation of x of n or xx of L evaluated at L equal to 0. The integrand in the right hand side is equal to the energy density spectrum. So, the integral over the interval minus pi less than or equal to omega less than or equal to pi yields the total signal energy. Therefore, E of x equal to or xx of 0 equal to summation n equal to minus infinity to plus infinity modulus of x of n the whole square into d omega equal to 1 by 2 pi integral minus pi to pi s xx of omega into d omega. Multiplication of two sequences. Windowing theorem. If x1 of n is related to x1 of omega and x2 of n is related to x2 of omega, then x3 of n is equivalent to x1 of n into x2 of n is related to x3 of omega equal to 1 by 2 pi integral minus pi to pi x1 of lambda into x2 of omega minus lambda into d lambda. The integral on the right hand side represents the convolution of the Fourier transforms x1 of omega and x2 of omega. This relation is the dual of the time domain convolution. In other words, the multiplication of two time domain sequences is equivalent to the convolution of their Fourier transforms. On the other hand, the convolution of two time domain sequences is equivalent to the multiplication of their Fourier transforms. To prove the given equation, we begin with the Fourier transform of x3 of n equal to x1 of n into x2 of n and use the formula for the inverse transform, namely x1 of n equal to 1 by 2 pi integral minus pi to pi x1 of lambda into e power j lambda n into d lambda. Thus we have x3 of omega equal to summation n equal to minus infinity to plus infinity x3 of n into e power minus j omega n equal to summation n equal to minus infinity to plus infinity x1 of n into x2 of n into e power minus j omega n equal to summation n equal to minus infinity to plus infinity 1 by 2 pi integral minus pi to pi x1 of lambda into e power j lambda n into d lambda into x2 of n into e power minus j omega n equal to 1 by 2 pi integral minus pi to pi x1 of lambda into d lambda summation n equal to minus infinity to plus infinity x2 of n into e power minus j omega minus lambda of n equal to 1 by 2 pi integral minus pi to pi x1 of lambda into x2 of omega minus lambda into d lambda. The convolution integral is known as periodic convolution of x1 of omega and x2 of omega, because it is the convolution of two periodic functions having the same period. Due to the periodicity of the Fourier transform for discrete time signals, there is no perfect duality between the time and frequency domains with respect to the convolution operation as in the case of continuous time signals. Indeed, convolution in the time domain, a periodic summation, is equivalent to multiplication of continuous periodic Fourier transforms. Differentiation in the frequency domain. If x of n is related to x of omega, then n into x of n is related to j into dx of omega divided by d omega. To prove this property, we use the definition of the Fourier transform. X of omega equal to f of x of n equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n, and differentiate the series term by term with respect to omega. Thus we obtain dx of omega divided by d omega equal to d divided by d omega summation n equal to minus infinity to plus infinity x of n into e power minus j omega n equal to summation n equal to minus infinity to plus infinity x of n into d divided by d omega e power minus j omega n equal to minus j summation n equal to minus infinity to plus infinity n into x of n into e power minus j omega n. Now multiply both sides of the equation by j to obtain the desired result. Table. Properties of the Fourier transform for discrete time signals. We can see in the table property, time domain and frequency domain. Table. Some useful Fourier transform pairs for discrete time aperiodic signals. Signal x of n and spectrum x of omega. Conclusion. In this chapter, the user would learn the following in detail. Frequency analysis, continuous time signals and discrete time signals. Properties of the Fourier transform for discrete time signals. Frequency domain characteristics of LTI systems. LTI system as a frequency selective filter. Inverse systems and deconvolution.